Hello everyone, welcome back. We now continue with the next session, AI and Modeling, Model and Data-Driven Approach. Welcome to the chair of this session, Paul Escapil-Inchauspé. It's very challenging. So.
Thank you, Monk. Okay, so now we can start this new session, one of the last sessions today, about data-driven and model-driven approaches, which is an area that has been surging and is a pretty hot topic over the last 5 years. So we start with a talk by Leopoldo Bertossi, who is professor and researcher at Universidad San Sebastián at the Faculty of Engineering, Architecture and Design. His research interests are in artificial intelligence, data science. In particular, he's been researching explainable AI, data management, causality, and computational logic. He's an emeritus professor at the School of Computer Science at Carleton University. He's a senior researcher at the Millennium Institute of Foundational Research on Data, and he's a researcher at Cinia. So welcome, Leopoldo. And today, so your talk will be about explainable artificial intelligence for classification and decision systems. Again.
Okay. Hello, everyone. I'm very happy to be here. Thanks for the invitation, for the nice introduction. And today, corresponding to the title of this session, I'm going to talk about some models for explainable AI, an area in which I have been working for the last few years. So I'm going to present research I have been doing relatively recently with some collaborators. I'm not going to mention many of them. Just I'm afraid of leaving us outside of the picture some other people, so I prefer not to mention anybody, I think. Okay. This is a situation we are confronting. We have a bank and a client who is applying for a loan at the bank. The client is E, is an entity that is described by means of feature values like the name, the age, the occupation, salary, etc. So it is an entity represented as a record of values for features, in this case name, age, activity, income, neighborhood, etc. Okay. So this entity requests a loan from the bank, which uses a classifier to determine if it is going to grant the loan request or not. So in this case, the answer is no. And the classifier, as you see here, can be something like a black box. You don't know what is going on inside, but this is the answer. And then the client has the right to ask why I deny the request. Yeah? So we would like to give explanations, and the question is here, what kind of explanation can we give for this answer, for this label? How, on what basis? Okay, there are different ways of approaching the problem. Yeah? So it is a very important subject in these days. The users are affected by results from AI systems, stakeholder request explanations. Yeah? We are affected by assessment, for example, credit scores, classification, good or bad client, decisions, approve or reject the loan, etc. So a whole new area of AI has emerged, that of explainable AI, and a whole discipline has emerged that involves also explainable AI, that is ethical AI. It touches several areas like law, sociology, philosophy, apart from computer science and AI itself. Yeah? The main purpose here is to have access to more transparent, trustable, fair, unbiased, and interpretable AI systems. Yeah. So here we are confronted again with this classifier. So what kind of classifier are we talking about? Right? That is it may really be a black box. In the sense that we really don't know what's going on inside, or it can be so complex that is, for all practical purposes, it is something like a black box. Yeah? And today, in a new legislation, forces AI systems affecting users to provide explanations and guarantee all the above that I mentioned before. Yeah? Well, of course, the search for explanations belongs to the nature of human beings. is a human activity. So that's a reason why addressing this problem from the point of view of AI is also relevant. Yeah? And this quest for explanation has been around since the inception of human beings. Right? Actually, ancient Greeks already were concerned with causes and effects. You can see in the work by Aristotle, for example, already concerns about causality. Yeah? This area has been studied by philosophers, logicians, physicists, and so on. So the question is are explanations a new subject in AI? It's a reasonable question since it is a very effervescent and fashionable subject in these days in AI. And the answer is yes and no. Actually, explanation has been the subject of AI for a long time as well. So they have been studying AI for some decades by now, and in related disciplines such as logic and statistics. So it's not something new, but there are some forms of explanation that are new in artificial intelligence, and I want to try to bridge the traditional approaches with the newer approaches. Yeah? So some others that are newer, let's say, have roots in already existing methodologies for providing explanations. Let me mention one of the traditional areas of AI that has to do with diagnosis, model-based diagnosis. So model-based diagnosis has been an area for some time. Actually, there are relevant papers since the early 80s or so. It is about doing a diagnosis of a system that is exhibiting some sort of unexpected behavior, using a model of the system and possibly a bit more than just the model of the system. So let me show a very simple example. Here we have a simple Boolean circuit. Could be a classifier because we have, in this case, features that are A, B, and C. They take a Boolean value, 0, 1. You have an AND gate, you have an OR gate, and then you get an output that is D. So D could be seen as something providing a label. Yeah? So if I input 1, 0, 1 into A, B, and C, actually, in this case, the circuit returns 1. And actually, that is what it should be. You should get a 1 with this circuit having an AND gate and an OR gate. However, the circuit is returning 0. So it is not working properly. Yeah? So why and what is wrong? I mean, that's what we want to find out. Yeah? Can we find a diagnosis, I mean, for the malfunctioning of this circuit? So what is the diagnosis? We have to characterize diagnosis first before giving an answer to these questions. We need the characterization, and that means giving a model. So this is the circuit again that is providing the wrong label, and then we can provide a model of the ideal circuit. This is just a couple of Boolean formulas that describe the circuits when it is working correctly. Yeah? And then we have the observation. Observation, we have A is true, B is false, C is true, and D is false. That is what we are observing. And what can we get from the combination of these two, the observation and the model of the circuit? Well, logically, using some sort of reasoning. That is the question. Well, since the combination is inconsistent because the system is providing the wrong answer, the wrong value, basically everything, because we have an inconsistent system, right? So basically everything is trivial, irrelevant, and you can get useless conclusions. Yeah? So we need a flexible model that allows for failures. Yeah? So we have to change the model a bit. We need, what I propose here is a weak model of failure, specifying things under normality. So how things should behave under normality, opening the ground for things to be abnormal as well. Yeah? So this is the model. Now this is saying when the gate A is not working abnormally, I mean it's working fine, then this gate behaves as expected. When the OR gate is not behaving abnormally, then this gate behaves as expected. So this is what basically the model is telling us. Now the gates could be abnormal or faulty. We have that possibility. So we need to change the model to get something useful out of this. Yeah? Now, the observation and the model is perfectly consistent because there might be things that are abnormal, and that is fine. So, but if we have the observation, the model that I just showed, together with the assumption that everything is working normally, I mean, that this is not, A is not abnormal, the OR gate is not abnormal, this is an inconsistent theory as before. And this is interesting because whenever you have an inconsistency, you can gain a lot of information from an inconsistency. Yeah, you have to take advantage of it. Yeah? So something has to be abnormal, and then a possible diagnosis just ABO. That means the OR gate is working abnormally. It's a diagnosis because making the gate O abnormal restores consistency. Now, when I assume that O is abnormal and the AND gate is normal, together with the rest of the model, well, we have a consistent theory now. Yeah? So we can say the abnormality of gate O, the OR gate, is an explanation for the malfunction of the circuit. Yeah? We can also an alternative that everything is working abnormally, both gates, is a diagnosis because making every gate abnormal restores consistency as well. Yeah? Of course, this is a diagnosis that is less informative than the previous one because here we are making everything wrong, right? So D is better than D prime. We have fewer assumptions, narrower, more focused and informative, yeah? Characterizations of malfunctioning. Yeah? So this is consistency-based diagnosis, and you can see this was introduced by Ray Reiter, I mean, in 1987. He was a prominent researcher in artificial intelligence with long-lasting contributions in the area. But we are talking about relatively old work. The question that comes next is the following. Can we assign scores to diagnosis? And that is something I'm going to talk about. Yeah? We are talking about weaker diagnosis or a stronger diagnosis, and then we can think of assigning some score, numerical scores, that tell us which are better as explanations. Yeah? Today, people are using in AI actual causality. Yeah? Basically, we have the same model. This can be cast the problem as a causality detection problem. We had the model as before, with the possibility of some components being faulty. And now, if we have the observation as before, together with the model, with the assumption that everything is abnormal, is not abnormal, that is working perfectly well. This, as we saw, this is an inconsistent theory. I just want to take a different, fresh look at what we had before. Yeah? So this is a logical equivalent to having, I mean, from the observation together with the model that I had before, with the assumption that everything is working perfectly, then I obtain as a conclusion D, yeah? that D has to be true as opposed to the 0 that I have here. Yeah? So counterfactuals now come into the picture. See, these are hypothetical changes or interventions on non-abnormalities into abnormalities to see if this implication changes. I want to see if by changing these values, making some things abnormal, I change the implication. I do not get the D anymore. Yeah? So actually, this is what it's the same example I had before, but seen from a different perspective. I have the observation on this left-hand side, the model, together now the possibility that the OR gate is abnormal, then I do not conclude D anymore. So this has been switched from being true to being false, or not being implied to not being implied. So we can say that this is a counterfactual cause for the malfunction of the system. Yeah? This is exactly what I have here. The abnormality of the OR gate is a counterfactual cause for the observation. Yeah? However, if I change the other gate, the AND gate, I still get the implication I had before, so this was not a switch. So we can say that the abnormality of A is not a counterfactual cause. This is not a good explanation for what is going on. So we can have some extra changes may be necessary in some cases. So if I change, this, nothing happens. But I need to change this as well, and this becomes a contingent change for the change I perform here. Now I do not get D anymore. That is what I want. Yeah? So we talk about contingent changes, changes that are additional to the main one that we are exploring. Yeah? So abnormality of A is neither counterfactual nor an actual cost, because the contingency of ABO, the abnormality of the OR gate, is already counterfactual cost that I already mentioned over here. Yeah, this is basically the notion of actual causality that was introduced by Joe Halpern and Judah Pearl in 2001. There are connections with model-based diagnosis between actual causality and model-based diagnosis that we have exploited in our research. I'm not going to say much about that. But what we want to do is to obtain some sort of attribution score, quantifying the strengths of a cause. Yeah? Causal responsibility is one that we have been using quite a lot. It was introduced by Chocolate and Halpern in 2004. And responsibility is an attribution score. It gives a number to possible causes. So in this case, since the responsibility of the OR gate basically by itself, switches the implication, it has the maximum responsibility. Actually, I don't need any additional contingent change. Just changing it by itself is going to switch the implication. Yeah? So in this case, it has a maximum responsibility of 1. In the case of the abnormality of A, as we saw, this is not a good explanation. We get the responsibility 0. So this is telling us, this cause is much stronger and better than this other one for the behavior of the system. Yeah? So we are going to concentrate in the rest of this presentation on attribution scores as explanations, numbers that give us an idea of how important, different components are for the label that we are obtaining from a system or the output. So there is actually a connection with causality based on causal network and structural models using AI. I'm not going to go deep into that, but there is a whole area of causality in AI. And there is, and actually what I just presented before, actual causality can be cast in those terms of causal networks and structural models. Basically, this is the causal network that you can use. Here in this case, you have structural models. You have some equations, associated to these networks, and basically this is the outcome, and these are the inputs to the system, and basically the system here is represented by means of this causal network. So important to mention here the distinction between variables. So the variables that are subject to analysis here are the so-called endogenous variables that are these two over here. Yeah? They can be subject to counterfactual intervention. We don't change everything, just those that are candidate to be good causes. Yeah? The others are called exogenous variables, and we usually concentrate on the endogenous variables. Well, I just mentioned this causal network involves a structural equation that you have here, but I'm not going to go deeper. I just want to show that these things are connected. There are different ways of approaching the problem. Okay, responsibility and explanations for classification. So the feature values get responsibility score, quantifying how much they contribute to the label. In this case, the output for the loan application, that was a no or a 1, let's say. Yeah? This method can be applied without necessarily knowing the internals of the classifier. That's interesting. We don't need to know, we don't have to know the details of the classifier. We can use them as a black box, actually, and we can still obtain reasonable numbers or scores or attribution scores. The classifier can be, if you want, treated as a black box system, and only the input-output relation of the model is needed to compute these scores. So in this case, just to come back to the example, given an entity E that gets a binary label, let's say 0, yeah, the question is, do changes of feature values or interventions on feature values change the label from 0 to 1, from rejecting the loan request to approving the loan request? That is the game that we are playing. So the idea is, this could be the initial circuit malfunctioning or not, or any classifier for binary features. You can play this game, yeah? Trying to switch the label by means of these changes of feature values. So let me show here a very simple example to show the gist of the responsibility score. Here I have an entity with a 4 feature, x1 up to x4, and then I get the label 0. I have no idea what's inside the classifier. Yeah? I want to know which of these feature values is most responsible for the outcome that we are obtaining. So in this case, actually, this is what I had at the previous slide. I get 0. I want to switch it to 1. then if I change this, in this case, the first variable from 1 to 0, I do change the label. This is good. That means this is showing that this has a very strong influence on the outcome. Yeah? So in this case, we can say that x1 equal 1 is a counterfactual cause for the outcome, and the responsibility is 1, is the maximum responsibility because I need to change only one value to switch the label. Now, in a second situation, now I keep the 1 I had, I change the 0 to 1, and I keep getting the 0, so nothing has changed. So in this case, we are concentrating on x2, is not a counterfactual cost because we are not switching the label. So now what happens here, basically, I have, I'm leaving this as it was, basically a 0 over here. I keep obtaining the 0 as before. But I'm changing now x3 and x4 from 0, 1 and now 1, 0. I don't change the label anymore. However, if in addition to these two changes, I change x2 to 1, then I do change the label. So I can say that x2, this value for x2, is an actual cause for the outcome that we had obtained before, but it needs a contingency set of changes that are the changes that are illustrated over here. Yeah? So the change of an x2 is accompanied by changes on x3 and x4, and thus make a change of label. Yeah? So in this case, we can say that x2 is an actual cause for the original output, but this is a contingency set for x2. These have to be changed as well. And in this case, basically, the responsibility is obtained by 1 over 1 plus the minimum size of a contingency set that has to accompany the change for x2. In this case, assuming that this is the minimum contingency set, we have this, the cardinality is 2, so this is 1/3. So this, in this case, x2 is an actual cause for the outcome of the system, but it has a responsibility of 1/3, as opposed to the one that had this one that had the maximum responsibility. And in this way, you can assign responsibility score, and you can identify which feature values are more relevant for the original label. Yeah? And we say that 1, 1, 0 is a counterfactual version of the original entity. I change some things over here, producing this, and this becomes a counterfactual version of the original input. Yeah? Counterfactuals are interesting per se, not only because you can compute scores. They are also interesting because they are very informative. I will come back to this. So back to our banking example, and now I had a no. This is the entity who got this label. The counterfactual version could be, for example, this one. I changed the age from 18 to 25, and I get now yes. Yeah? So that means it's a very strong, the age was a very strong cause for this outcome. Yeah? So the value for feature age is a counterfactual cause with explanatory responsibility of 1. Yeah? Now, if I take the original entity and I change now the salary and the neighborhood where this guy lives, I get yes. I also change the label. The value for income is now this one is an actual cost with responsibility of 1/2 because I need an additional change over here. Yeah? That is the reason why it's a weaker cost. Yeah? The question is really, actually, we should question what we are doing here. In the previous example, I was changing zeros to 1 or 1 to zeros. In this case, I changed 18 to 25, but I could have changed 18 to 27 or 30, 44. This is when you have more values, each feature can take more than 2 values. I mean, this is the idea. Something like this should happen, but we have to take this more seriously. Actually, for binary features, the previous definition of responsibility works fine. In the case of the classifier, possible many new values for a feature do not change the label, and a few of them do. So maybe there are 18 changes to 25 will change the label, but if I change 18 to many other values, the value will not change. So that makes us doubt whether 18 is a good cost or not. So we need to change this a bit. I'm not going to go into details. So the original value is not a great explanation in the case when you have possibly many feature values. So what we did with some co-authors, we generalized the responsibility score in order to take care of situations where we have multiple feature values. Yeah? So the idea, the intuition is better consider contingent features and values for them, and consider an average of the labels, because you have possibly many different labels for different values of the feature. Yeah? So we are considering binary classifier with label 1 or 0. So assume label 1 is the one we want to explain. Yeah? But the features can take different values. So the responsibility, as I mentioned before, is a local explanation score. For feature value in a particular entity is local. This feature has this responsibility. It's not a global responsibility. It's a local explanation score. And the generalized responsibility, I'm not going to go into details. Basically, the change becomes much more complicated. By basically what I'm trying to show here is that the generalized responsibility score will take into account all the possible features values. And two things are relevant to mention here. That we have to end up solving an optimization problem because we want to find minimum contingency sets on one side. And the other thing, we are considering average labels. So we have expected values. So what is the bottom line? Basically, we need a probability distribution on the entity population. Yeah? So these make things much more complicated, but this score behaves much better when you have features with multiple possible values, not only binary values. Yeah? When you compute the responsibility score, I mean, this requires multiple passes through the classifier, yeah? Because you can have to consider all possible different values for the features. So, and also, as I said before, you need a probability distribution on the entity population. And several probability distribution can be used. This is quite a relevant issue. I mean, what distribution do you use on the entity population? I'm not going to say more about this, but this is a very crucial point. There are some papers here where we investigate the problem. In our experiment, the RESP, the generalized version of the responsibility score, was computed with empirical product distribution. Yeah? And we are usually interested in maximum responsibility feature values. They are associated to minimum cardinality contingency set. You want to change as few other features as possible. It is possible to prove mathematically that the problem of computing the RESP score, the binary one and the generalized one is intractable, as an intractable problem. Responsibility does not require the internals of a classifier. The question that we ask is, can we compute the responsibility score when we have access to the internals of the classifier, when we have more elements to play the game? Also relevant, what can we do with the high responsibility explanation? What can we use it in some sense? Well, the issue here is that some counterfactuals may not make sense or be useful. Yeah? In the example, changing the age, I mean, basically from 18 to 25 makes the applicant to the loan, I mean, wait for 7 years. I mean, may not be feasible. It's not something interesting. Maybe changing job and neighborhood could be done. It's feasible, something that is interesting to explore. That's why I was saying that counterfactuals by themselves are interesting. So we may want to obtain actionable explanations, or what is called a resource. Basically, those are counterfactuals that allows us to do something in practice. Yeah? So we want a specification, and reasoning with counterfactual can be useful. If I have time, I will come back to this, but here is very important to have the possibility of doing some sort of reasoning on counterfactual or with counterfactuals. I don't know if we'll have time to tackle this issue, but I hope you get the feeling that this is an important part. Let me mention another score that is very popular, that is SHAP, is widely used in the area of AI in these days. It's based on the general Shapley value of coalition game theory. It's a popular measure of contribution of players to a coalition game. And for each application of the Shapley value that's completely general, you have to choose the appropriate game function that maps subsets of players to real numbers. Yeah? A sub-team of players gets a real number. Yeah? In this case, in our application, I mean, the set of players basically contains the features or the feature values. Yeah? You want to see which of the feature values contributes the most to the outcome. Yeah? And we can use the Shapley value to obtain that. So in this case, the gain function that is used is the expected value of the label, and it's an expected value of the label, basically. And this is the formula. I'm not going to go into the formula. is basically the incarnation of the Shapley value using this particular gain function. Two things are important to realize. First, we need a distribution because it is an expected value. And we are considering all the possible subsets of the features. That means we are already creating right away an exponential combinatorial explosion. Yeah? So that is an issue because maybe this is not going to be computable efficiently. Yeah? This SHAP score has become quite popular. It was introduced in 2017, and it assumes a probability distribution on the entity population, and requires also multiple passes through the classifier because you have to compute labels for all kind of modify or intervene entities. So that made us ask ourselves, can we do something better, when we have an open box model? Yeah? And SHAP has become the most popular explanation of score in machine learning. The Shapley value, in particular SHAP, is provably intractable. One can prove mathematically that is a hard problem. Yeah? Can we do better at computing SHAP with an open classifier when we have the elements inside, having access to the extraction of the classifier and the components? So we are moving away from this black box, and now we have a classifier that could be, for example, this decision tree, something like this. Can we do better or not? Well, we have proved with some colleagues here in Chile, Pablo Marcelo Arenas, and Miquel Monet from Inria in France, that SHAP is extractable, can be computed in polynomial time for deterministic and decomposable Boolean circuits. There are circuits of this kind that have a particular shape. Now, I'm not going to go into the details of the kind of circuits. They are binary classifiers, and we use the uniform or product distribution because we need distribution for the Shapley value or the SHAP score. Yeah? But you can say, well, who cares about this kind of circuits? Well, the issue is that we get tractability right away for SHAP for a vast collection of classifiers via the technique of knowledge compilation. Yeah? Basically, we obtain tractability for decision trees, even for non-binary decision trees, ordered binary decision diagrams, sentential decision diagrams, etc., a whole family of classifiers that are interested in the AI literature. Yeah. And then the question that we pose ourselves, what happens if we try to apply this methodology to something that is not a decision tree, but something really more complex, like a neural network? Yeah. So SHAP on binary neural network. Here we have a binary neural network. All the inputs are binary, not necessarily the weight function. That can be any real number, basically. So neural networks are basically considered as black boxes, are really complex things, and so usually we don't go into the details, in order to find a responsibility or SHAP scores. But we experimented with the SHAP computation on a binary neural network via compilation into one of the circuits that I just mentioned in the previous slide. So actually, I can transform this network into this Boolean circuit of the kind that we investigated in detail, and it follows a procedure. Basically, this neural network is transformed into a conjunctive normal form, a logical formula. The conjunctive normal form is transformed into a sentential decision diagram, and the sentential decision diagram is straightforwardly transformed into one of our circuits. This part is the only one that is non-polynomial, but can be somehow controlled, managed. Yeah, is what is called fixed parameter tractable. So it is not, it's not necessarily a bad idea to try to apply the SHAP score for this kind of circuits when we start with a Boolean or binary neural network. So why? Because, well, here there is an expensive step, but this, once you obtain your final circuit, you can obtain all kind of explanations using this circuit. And the computation of the circuit is just a one-shot computation. So, and then you can use it multiple times. So maybe it is worth spending time of that. Yeah? So we experimented, for example, with a binary neural network with 14 gates, and actually the circuit, the resultant circuit is relatively large, right? And we compare SHAP computation for the black box here, neural network, and the open box circuit that we obtain from here, and also using this as a black box, but this part is not interesting. This is the comparison that's interesting, using this as an open box versus using this as a black box. And we compute the sharpest score for all entities with increasing numbers of them. And actually, this is the figure that we get. This graph shows in blue the time where we need to compute all the sharpest score with increasing numbers of entities directly on the binary neural network. And this in yellow is what we obtain, the time that we need to compute the same, but now on the open classifier. This is logarithmic scale, so you can see that this is really an enormous, gain. So this is really worth exploring. This is our, and there is a lot of work to do here, but this is already very interesting, I think, that you can apply this mechanism to do some sort of a fast sharp score computation. I'm going to finish. How much time? I need a couple of slides. How I'm doing? Okay. The need for reasoning. I mentioned before the need for reasoning. I think it's important. I mean, I want to go beyond just computing attribution score, either responsibility or sharp score. There are many of them around. So questions that naturally arise are the following. What can we do with attribution scores and counterfactual explanations? Apart from the obvious, that seeing that we get a score and changes the label. What else can we get from that? Something more. Yeah? We can reason about or with them, analyze them, select some of them, aggregate them, etc. You can do many things with explanation. Actually, you can think of learning from the explanations themselves. It's something like a second step of learning. Yeah? We would like to see what happens in interaction with both attribution score or model or algorithm or classifier for further exploration. So reason about counterfactual in the presence of the classifier, to explore further each of the features that are participating in the game. That is for global understanding of the classifier or application domain, either way. So we need tools for conveying or imposing domain knowledge. That is very important. What I have presented so far doesn't use any kind of domain knowledge, any kind of domain semantics. That is very important, and this is an area that has been relatively neglected, and I think there is a lot to do in that direction. So we need tools for conveying or imposing domain knowledge or domain semantics. For example, an age never decreases, right? So you're never going to make someone who is 17 years old, 15 years old. That doesn't make any sense, right? The models I presented allow that, but that doesn't make any sense. So only some counterfactual may make sense. Some combination of feature values may not be allowed, for example. Maybe change the age of the person to be 5 years old and be married at the same time, for example. Right? So, and some changes might trigger other changes. These are all kind of things that are not being explored, involved into a score computation. Or we might want to impose preferences on counterfactual. I want counterfactual that change these kind of features and not those others. So there is a lot of room for reasoning here. So we need tools for doing this kind of logical reasoning. We need tools for posing and answering queries about explanations. Are there explanations with this particular property, for example, or any two that differ by these feature values, for example? Those are all interesting questions that people have not addressed satisfactorily so far. For example, we want to specify high score actionable explanations that are useful in practice, and possible computation only them, those that make sense in practice, or others that have a different preferred property, right? We can do this on the fly through an on-the-fly interaction with different machine learning models and scores. Do I get the same score with this different machine learning system? We need to reason about this and possible in interaction with different classification systems. There are many things to explore. For example, we would like to impose condition on features value. As you see, I'm about to finish. Imposing condition on feature values. What if I leave some feature values fixed? Do I still get some interesting counterfactuals that have a high score? That is the natural question. Do I get the same high score feature with this similar entity, right? And you can specify similarity of entities, logically specify. Is there a high score counterfactual version of the entity that changes this specific feature or never changes that other one? Those are all valid questions. Actually, we have done something along this line. It's not that this is completely virgin territory. So we have devised declarative, means logic-based method to reason with and about counterfactual and compute at the same time responsibility scores. We have done this in interaction with classifiers that are called from the program. Yeah? And we have used ancestor programming, that is a form of logic programming that is particularly suitable for this kind of problems, but I don't have time to explain why that is the case, but it's a form of logic programming that is very powerful in these days. So this combination of logical reasoning with classifiers, for example, it could be a neural network, actually goes very much in the direction of neurosymbolic AI, that is one of the most interesting areas of artificial intelligence in these days, in which there is a lot of activity and many things to address and tackle. So this is an invitation to go into these kind of problems. There are many interesting issues to explore and investigate. I think I'm going to stop here. Thanks a lot for your attention.
Thank you, Leopoldo. Are there questions here? Questions? Well, I go for a few questions, but it's not working. Is it working? No? Yeah, I try another one. Hello. Well, just two questions. That I'm not an expert here, and for example, so if you take a general feed-forward neural network, so you used binary neural network, but if you go to a more general neural network, you cannot do any reasoning.
Well, okay, so sorry. We haven't done anything with non-binary neural networks. I think what we have in mind is to go through binarizing a non-binary neural network as an approach to explore. But what I present is quite recent work, and I think there is a lot of work to do. But that would be my first approach, to try to binarize a non-binary neural network and try to apply this kind of approach and see what happens. But we haven't done that yet. But it's a very reasonable question, of course.
Well, to keep on the question, Luis, yeah, I go for one. And also, I'd like, it's maybe two comments, but I see that most of us have been using all these Shapley values and so on because it's very easy to use. So I don't know which is your opinion about that, about the fact that everyone is using the same method. And another question is more about, in practical cases, sometimes I've been comparing different models. And the Shapley value, for example, was giving very different features importance. Some features were very important, for example, for the gradient boosting, and then you get to the neural network, and you see that the features are changing a lot. I don't know if you have any explanation about that, about what's happening.
Well, I think, well, people are really, they are using Shapley value are omnipresent in these days. And there are actually different open platforms that compute the Shapley value that people can use, and people are using them. But I'm not sure that this is the end of the game. As I said, there are many issues that have not been explored. For example, how can we exploit, even with the sharp scores, I mean, the use of domain semantic, domain knowledge. I mean, there are many things that have not been explored yet. And actually, there are some people who have criticized, I mean, the sharp scores and have proposed other scores. I mean, I mentioned a couple of them, but there are also sufficient scores, I mean, or abductive explanation that have been proposed as an alternative. And I think that this is, I mean, we have a very fluid situation, as the politician says. Yeah, as actually, things have not settled down yet, I think. And even with, if you want to apply a Shapley score, Shapley values, you still have to, there are many things that have to be done and explored. What comes to my mind naturally has to do with the use of domain knowledge, domain semantics that could give better results because we are using additional knowledge, not just data, let's say. I don't know what else. I don't know what's going to be the final stage, I mean, of all this. This is a moving territory.
Well, thanks, Leopoldo. By the way, thanks for coming after you have had a very, let's say, personal, intense week. So my question was actually very similar to the one that Paul just posed, in particular because we have these gray boxes that are neural networks that I mean, you can read them. Yes, the light is very. Maybe if you give the mic.
Sorry, I got a bit lost, and also the light.
Yes, I know.
I was just operative.
If you want, you can move out of the light.
Of cataract, so the light is really bothering.
So the question is, well, first, Paul already covered that. Part of my question is, how do you felt about this uniformity of people using CHAP values as it is solved, you know, without. I'm going to put a nice CHAP value plot in my paper and move forward. And we have this, like, what are the risks of just using CHAP values? And I think you already answered part of that, but.
Well, actually, we have been, I have been doing some work with a student of mine, quite recent work. I just submitted another paper I'm about to submit. We have been exploring, I mean, comparing CHAP scores with other scores, for example, with the responsibility scores or the causal effect score that I didn't mention here. And actually, it's very interesting because you can actually find conditions under which, I mean, different scores are at least aligned, which is something interesting to identify. Maybe you don't get the same numbers, but at least you get the same rankings, right? So there is a lack of more fundamental work on, in terms of comparing the results that you are going to get from different scores, because there are several around. Yeah? But if you know that under certain conditions, these two scores are always going to give you the same ranking in terms of importance, right? That is something that is useful. Yeah? So that is something that is useful, interesting to explore. As I said, we are starting to scratch the surface in that direction. But we have some interesting results that guarantee at least that the rankings are aligned. And under certain conditions, you find examples where they are not. I mean, so there is a lot of research to do in this area. I mean, there are many open problems. So you're right. I mean, people are just using CHAP values and then they move on, right? I mean, that's the final story. But I don't think it's necessarily the final story. I mean, one has to be honest. I mean, and scientifically honest. I mean, what I'm trying to say. And see under what conditions on this particular scores is reasonable, applicable, with some guarantees. Right? I don't know what else to say. I mean,
yeah, no, but thanks. It was good to me. Thanks.
Well, thank you. Wait, yeah. Okay, there is one question from the chat. So we have a question from Rodrigo Vargas asking if mechanical interpretability could be used to validate the fidelity of explanations generated by XAI methods. So can you use the mechanical interpretability to try to explain how the XAI is working?
Well, two things. First of all, I have no idea what is mechanical interpretability. I really don't know what it is. I mean, but one thing, I mean, that I would like to mention in this context is that people tend to confuse explanation with interpretation. And that is something that is fundamentally wrong from my point of view. Explanation is what I just introduced, and what I introduced here, presented here, is just one form of explanations through scores. They are not the only kind of explanation that you can propose. But interpretation is a much subtler problem. I mean, what does it mean that the machine learning system is interpretable? That is a different question. That is completely, actually, I don't think there is no really satisfactory answer in the community about what is an interpretable model. In my view, what you have to do is to play a completely different game. You have to, for example, map your system into some sort of, for example, ontology, yeah? An ontology that explains things in the terms that are useful for whoever is using the system. And that, for me, would be an interpretation. That is what you do in interpretation. Interpretation in science is a mapping from one thing into another that you understand better. So that is not necessarily explanation. So interpretability, for me, is a different game. And it has not been properly addressed so far, in my view. And there is a lot of work to do in that direction. I have some ideas about how to proceed, but it's not... I don't have the final answer yet. But about the mechanical interpretability, I don't know what it is really.
I don't know either. So, well, I think it's a good way to conclude on this session of questions. Thank you, Leopoldo. It was a very good talk.
Yeah, thank you again.
And now we'll keep with our next talk in this session. By Andrés Sepúlveda, who is Associate Professor at the University of Concepción in the Department of Geophysics. Andrés today will be with this next talk, which is titled, the title will appear very soon, I do not memorize it, about fishermen, current developments in numerical modeling of Chilean Patagonian waters, opportunities for AI applications.
Okay, good afternoon. Thank you for coming, and thank you very much to Inria for the invitation. I must confess first that almost 30 years ago, I was a young and proud physics student, and one of my professors came to me with a book, of course, the photocopy of a book with spiral, and told me if I wanted to work on this topic with him. So I read this book that was full of circles and arrows between the circles, and say, there's no physics in this. This is not real physics. So I told him, I don't want this topic. So now I'm coming back to understand the opportunity I was offered at that time and trying to learn some combination of my work with neural networks or artificial intelligence. Well, okay, I want to focus as a side subject of my work, the area of Chilean Patagonia, between Puerto Montt and Laguna San Rafael. This is the area we start to study. And there's a lot of research in that area because it's very interesting, it's very important in terms of aquaculture, all the activity that is being developed there. And as such, there are big challenges to it. You have channels, you have fjords, you have very large tides, you have the discharge of rivers, of glaciers. So in terms of physics, it's very interesting. In terms of economy, it's very challenging. We want to understand the circulation. We need to understand the rivers. The rivers are an input of nutrients. But the nutrients depend on the agriculture. If you have land, if you have harvesting something, you have cattle. So it's really a complex physical and social area of interest. So to really understand it, we are still with big problems. We need a bigger boat. We need a bigger computer every time we want to do something. And part of the objective is to see how much can do AI techniques help us to overcome this problem. My tool of research is a numerical model of the ocean called CROCO. And as you can see, these are all different models that exist on numerical modeling. Well, there are many, many models. One of my professors also told me, don't make your own model. We have plenty. but even now that happens. In particular, Croco is a mostly French development. It's the work of several institutions, INRIA among them. And we have done a little bit of work at Concepcion to support Croco. It became one branch of also another big model concept as ROMS from Rutgers University. But with the work of Patrick Marchesiello from IRD, when he was working with McWilliams in Los Angeles, it became its own branch. And it became its own branch thanks to the input of Laurent Debreu from INRIA, who gave this AGRIF contributions to ROMS. And at that time, that really made ROMS, this branch of ROMS, a whole different model. Like it gave me a new strength that it was very attractive. And this AGRIF, for those another area, means it's a way of refinement, how to deal with smaller scales in your area. That's part of the complexity, for example, in the fjords. You want to study the ocean, but you're going to go transition into the fjords, so your scale, your physical scale is changing. But thanks to this work, this became a big player on what is numerical modeling. And some years later, this model became what is now Croco through the integration of different models from Europe and mainly in France, where there were several models being developed, and there was a consensus of working one model rather than to have too many small models. So that's the main tool of our research. So this is the main page of the numerical model. We are now on version 2.01 already. And it's open, so you can get at INRIA GitLab. You can get the code and all the different tools there, if you're interested. And as a good model, you need boundary conditions, you need initial conditions, and many times you can get them from this, also on your European service, very, very useful. So the title of Fisherman, it all started with this ISA virus crisis in Patagonia, 2007, 2008. One of my colleagues who lives in Puerto Montt told me there is a problem. The industry wants you to apply for a government-funded project because there's an emergency. I say, well, that's not an emergency. If you want to apply to funds from the government, you want the government to pay for it. It's an emergency, you pay for it now. And it was such an emergency that the industry paid for the support of this project, a salmon company. And so we did numerical simulations because what used to happen, this is the Aysén Fjord, this is Moralidad Channel. We wanted to study the dispersion of this virus among the different salmon centers. And as you can see, the area, at some point, the area was divided in management areas, sub-areas. And as you can see, the dispersion of the virus does not obey or straight lines. This is when you divide a country with straight lines, and years later you have wars between the countries because that's what the culture was. And our main point was, okay, you need to understand the hydrodynamics if you want to avoid the spread between this center and this other center. So we need this as an input. And now this model, Croco, as a regional model, has its own limitations. There are scales you can deal with. There are things you can deal better with other models. And in a collaboration with Pablo Cornejo from the Mechanical Engineering Department in UdeC, we did a work on adding CFD codes, ANSYS Fluent, to get a more detailed study of this area, of this fjord, part of a fjord, where we can represent the actual salmon cage and the effect it has on the currents. This is more like a porous media approach. So the topic here that hopefully is an area of development we can support with artificial intelligence is how do we go into finer scales? How we can do that? Now, we have this tool from Croco, this aggregate refinement. We need to add several models to get to the appropriate resolution, and even then, we need more. So can we do that in some way? As area of research, the Fisheries Institute here in Chile, IFOP, has this very nice website, a very nice project, Chonos, who gathers all this information about the area. So you have this here, the numerical model, the ocean model that is fed by the atmospheric model. You have a Lagrangian particle module. You have real data. You have a contribution from rivers. And I think it's not shown here, but also you have a recent addition that is the contribution from the salmon buoys. The government demanded the salmon industry to add buoys for observational information on these areas. But all of this here, this is a sort of source of real-time data that we need to use with our models. Right now, we can use them to compare. There's a transitional point where we want to do data simulation we want to see later. So this is a nicer picture of what is available. So this is the actual modeling area. We have something similar, or they have something similar for the Magellan region. And one of the previous talks, there was a mention about one of the lines of research of this institute they had was the front end. And this is very important also in oceanography. We need to present the data, the information, the model results in a way that is more friendly with the community, with the people, and this is one of the best examples I've seen. So we need to improve the public access to the information. Since one of the main topics in this area is the aquaculture industry, and one of the problems they have is harmful algal blooms. We have done some research on the biochemistry of this area, how the different components behave and relate. We have some improvements. We have some time series of data that are adjusting to the observations. But the main limitation is in opposite case to astronomy, the oceanography is mostly is poor on data. We don't have a lot of information. So to feed our models, to validate our models. So I think in the context of artificial intelligence, we're trying to use the models as a source of information, or best dynamically consistent source of circulation, nutrients, temperature, for example. But we're working on this topic. We have the hydrodynamics more or less well understood. We need to go to finer resolutions. But now the next frontier is biogeochemistry. And also with collaboration with France, Patrick Marchesiello again from IRD, we started to do a 3D bar assimilation code for ROMSA grid as it was then. And luckily, it's now coming back to as an important topic into Croco, and we will try to implement this into this operational model from IFOP to see they can actually assimilate the data into the simulations and improve the forecasting of the circulation. Besides data, I think the greatest limitation we have is people. We don't have enough people with abilities in numerical simulation. The Croco community is offering training sessions we do them in Chile, they're doing it in South Africa also, but we don't have people with knowledge on oceanography, programming, modeling, And now we need people with the knowledge on artificial methods, artificial intelligence methods. But we're working on that, and we're now in our 5th summer school. It will be in January in Valparaiso for basic oceanography, and in Concepcion for forecasting. The goal, the one project we admire, at least personally, is what they have developed in Norway. It's a similar problem in the sense you have a complex coastlines, plenty of fjords, and instead of doing one model here, one model there, my model is a little to the left, my model is a little to the right, I study this fjord, I study this fjord. They make one big model after many years of government-supported funding for the whole area. So they have the whole coast at 800 meters. The pixel is 800. So it's great. So that's one example to follow. And I think in terms of artificial intelligence, we need to know if they're thinking something. I will look at them as an example, say, how do you plan to integrate this? How is this being helpful for that? For understanding the circulation and the dispersion of infection in their fjords. It's very, very nice work. Because we have seen these examples, I mean, in the last several years, there's a lot of talk of artificial intelligence, on this artificial intelligence model. And I think the greatest advantage I've seen so far is that they are really fast. And fast is nice, but I mean, I need a bigger computer to be faster only. But it's nice, and it's a very good contribution, especially if you're doing operational oceanography. You are limited to, you need to get your results on time before tomorrow 8 a.m. So yeah, these are good. We don't know why they work well. We don't know yet when they fail or how they fail. That's my physics background bothering me, and we should know that. But yeah, this will be a great contribution to get faster and higher resolutions for especially this area that are very poor on data. So it's interesting, and this shows something that is happening also in oceanography. We are always following the lead of the atmospheric community. All the numerical developments in atmosphere forecasting, atmosphere data simulation, you'll see them like 10 years later in oceanography. It's a smaller community, but if this happens in atmospheric modeling, I'm sure we will see this more or less in 10 years in oceanography. So what have we done from the numerical modeling part in Chile, in Patagonia? We have several years of experience, more than 10 years, modeling the area, understanding, fixing the bathymetry, fixing the coastline, adding the rivers. So there's a big, a large experience there. We have several institutions working on this. We have critical mass from the oceanography part. This contribution has an impact at the regional scale. We are being able to support communities in Peru and Colombia, a little bit in Mexico on numerical modeling. We have advanced in the effect of rivers into the model. That's something that was not incorporated in the earlier versions. Now there's a product from IFOP, Flow, is called, who gives you a better time series for rivers. The biochemistry is an active area of research because we need to predict or understand the area of effect of harmful algal bloom. The highest concentration of toxins are those that we get in Chile. And data simulation is the closest to this we have we're close to include it in this process. And we have operation forecasting, and currently we are applying to a research project, hopefully we will know in a couple of months if it's accepted, to add the effect of glaciers that are also a very important contribution of fresh water, not only rivers, but glaciers in the Chilean fjords. More in the Magellan region, but we have a couple places in Glacier San Rafael, Laguna San Rafael in this region. What do we want? What was our wish list for artificial intelligence for the oceanic community? Our models are very slow, very slow. And when you get a good model, then we're dealing now with pixels of 100 meters, and people want tens of meters. And that is a large increase on computational time. So we either get the same results from the atmospheric community, or we expect the quantum computers that will calculate everything in an instant. I don't know. So if we want to do data simulation, because right now we're feeding at the boundaries, things are more slower. Can we use AI for this? And this is where the physics part of neural networks may be interesting. Hopefully this will help. And we need to train more training on artificial intelligence methods in geoscience to be able to talk with each other, to understand what they're doing. This is something that's lacking in most of the curricula in the schools. So we need work on this line. And, well, my complaint is, physics is, when you have a model and you include physics, you say, okay, it's great, I understand what is this, but your model only has the equations that you understand. So the model only has what you put into it. So one of the advantages of these methods of artificial intelligence, you can see emerging patterns that you were not expecting. And maybe we can use that to understand what are the main drivers in biochemistry fluxes, contributions that are in the data but are not being in the model, represented explicitly in the model. So, well, thank you.
Thank you, Andrés. Very good talk. Are there any questions here? There is someone.
Thank you. Maybe they're not really applicable, but have you looked at not AI-based like model order reduction techniques or data simulations, like POD-based methods?
We haven't yet, and we're not. They're not. It's a large community of modelers, but we don't have too many people, so we need someone to free their time and work on it. We're still starting to do real data simulation because now we have data enough to do data simulation, but other methods we haven't had the time to apply yet.
Thank you.
There.
Hi, thanks for the talk. I have one general question and one specific for Croco. The general question is, what are the main challenges for ocean modeling considering the climate change and the drastic events occurring in global scale? And in specific, if Croco is prepared to, I don't know, abroad these challenges?
Well, when you have in the classical framework, you have your model, you have the physics of the model, and you need boundary conditions. You need an initial condition and boundary conditions to fit the model on the boundaries. For climate change scenarios, the main challenge is we don't have very good models of the future. We have some models, and there are many models, but we don't have a good understanding of which one is the good for Chile, because most of these, or all of these climate change models are global. That means they may work well on average, but they may do poorly in Chile and very good in Europe, so they say that's okay, or the R score is good. So we need first to understand which is the model that we can use on the ocean and on the atmospheric side for your area of interest. So the boundary is key for the physics. And which model of the many available we don't know yet. In that context, CROCO is a model more, well, it's a computational constriction, because you want to study climate change, you want to study hundreds of years of circulation changes. And with the current grid size and current time steps, you can think about decades, but hundreds of years is, we don't have the computer or the disk space to be able to do that. So it's more a logistics problem, limitation, but this model, CROCO, as many others, can be used because the physics is there. We have the right equations, the equations we know. So all the models I showed in the first slides, they're all very good. It's not that CROCO is much better than the others. There's no secret physics for ocean dynamics. But some are more friendly, some have a larger community, but the physics is, the same physics is in most of them. But boundary conditions are the big issue.
Okay, and to finish, actually, it's almost the question I was going to ask you. It's a comment by Antoine Rousseau saying, thanks, Andrés, very nice talk. We need models to produce data and AI to improve models, in particular when models are not mature enough. So maybe you can comment on what Anton said.
Can you?
So, yeah. He said that first we need models to produce more data, and then we need AI to use this data and to improve the models and everything.
Yeah, that's a very good point, because we were working with some students in a project about that. We want to predict in terms of days or weeks at most an algal bloom. We need information on radiation. We need information on the circulation, the temperature, and well, we don't have information of the future. And we need models that, we have satellites that can observe daily, but satellites are blocked by, for example, clouds. So at this point, models are a very good resource of creating time series for the future. And we can use them to feed these data-intensive artificial intelligence approaches. So that's the current use of numerical models. I think we can, a good understanding of the past, we can predict up to, say, 5 days with some confidence. And this can be used to predict these oxygen loss events that are very harmful also for the aquaculture.
Well, okay. Thank you, Andrés.
Thank you.
We can...
Well, I am going to introduce the...
That's fine.
Sorry, I got disoriented. So Paul is also presenting today. Paul is a new addition to the Inria team. So Paul, you are also the session chair, so introduce yourself.
Yeah, I think it's easier. Well, thank you. Today we'll dive into a subject that has been mentioned a lot of time during these 3 days. So it will be about a paradigm that is data-centric engineering and scientific machine learning. So I try to discuss, show a few results, some works of mine, and explain a little more about those topics. So we can start with this definition about all these data-centric paradigm. It's interesting because these are notions that have been emerging over the last years. So among communities, people are going to use that definition, other definition, and so on. So I start with these two definitions that are at the end at almost the same definition. But scientific machine learning is this area that has been emerging over the last years, which tries to combine physics into machine learning models in general. So you have, in general, data-driven, data-based formulation. You can have model-based formulation, which could be PDEs and other information. And everything is about how to combine everything, how to combine this information. And coming back to data-centric engineering, there is a very interesting paper here that I mentioned. You cannot read maybe, but that is about almost the same definition, but this data-centric term can be like more than just engineering, and I will try to discuss about that and to explain that before we move to all these scientific machine learning applications. So, very simple diagram. This is the kind of diagram that you can see in a lot of companies, for example, who are speaking about all this decision making, and you have to use data to take your own decisions. And this is the classical sequential approach. When we have the data, we create a model over it, and then we take decision, and we use, for example, data visualization. It can be business intelligence and so on. But in the case of the data-centric approach, you try to put the data at the heart. It's like the main component of everything, of all your organization. So it can apply to companies, it can apply to science, it can apply to all these applications that we are doing. There is like a strong relationship with what we were discussing just now. We have models that can be quite slow. We want to accelerate models. But if we want to accelerate those models and use AI, for example, we need good data sets. We need good data, and it's not that easy. So in this type of paradigm, you have your data, and then you use it as the skeleton of everything you're doing, and you can connect. Well, the data will be fed by IoT, for example, which is another big challenge. And you connect to models, you can take decisions, and you have all this good ecosystem that you can create. So you see that this data-centric engineering, this concept at the end is something that is pretty deep. And I wanted to just introduce that because I find it very important. And why is it that important? It's something that is inside the mission of Inria Chile and Inria in general, and all this community that is here, is that there are a lot of new tasks. If you want to have all this data-centric approach, you need people that are good at simulation, you need people who are good at DevOps, you need people who are good at data governance, data sets management, and so on. So you see, this is all these new tasks. In general, it's pretty hard to be good at everything, so all of us are trying to learn, and this is how this ecosystem is. So getting back to scientific computing, we can try to do this difference between the traditional methods, who have been like the methods that engineers have been using for a few decades. You have the finite element method, spectral methods. I'm coming from the boundary elements methods community, for example. And these new methods that are more ML-based, with the pins that have been mentioned a lot today, for example, physics-informed neural network that I tried to introduce a little better, and other techniques such as operator learning and so on. So, as an abstract PD problem in numerical analysis, I want to start with this abstract setting, the very simple setting like of time domain PDE. So we have a boundary value problem posed over a domain with initial condition, boundary condition. In this case, the operator n can be nonlinear. And I put this lambda parameter that can be like a parameter of the system. It can be the wave number or other thing. So in all these inverse problems, you try to find this parameter. Sometimes you have missing information. So it's a way to try to represent the problem over a quite abstract framework. And with this classical abstract PDE, If we have, for example, an unknown material parameter, we can try to use traditional methods, such as adjoint method, when you have ways to calculate the gradients and to get into a solution that will be using all this observation that you have. Other example, if the problem is nonlinear, there is a lot of theory and theoretical guarantees if you use Newton method, for example. And to finish, it's an area I've been working on, like in uncertainty quantification and so on. If you have very high dimensional problem, you can use fast quadrature and try to represent your problem in another way or faster way. So, well, this is the traditional part. And what is interesting, and this is why maybe people are talking a lot about these pins, for all these kind of issues, you can get a unified formulation as physics-informed neural network. It will not be much harder to implement. Implementation is pretty easy in general. It's all that's happened with the neural networks. So that is why it can be an interesting solution. So how physics-informed neural networks work? It's just that you will use this PDE, the solution of your PDE, and you will try to approximate it using a neural network. So here I have a very simple feed-forward neural network that will try to approximate the solution of the PDE. I have a PDE, I have a neural network, I have to define the loss function. So how does it work? In the case of, for example, a forward problem, for example, I could use a typical solver, traditional solver. In this case, I have to define collocation points over my domain. I do the same for boundary condition, initial condition. So over my entire domain, I will define these points where I will evaluate the loss. And if I have observation, if I am in the case of an inverse problem, I can do the same with the observation. So I have my data set of observation. I define a data set of collocation points over the domain, the boundary, and the initial condition. And I use my neural network to solve the problem. So I introduce the training data sets, and it gives me this kind of loss functions where you can see that you have many terms in this case, but the first term will be the residual over the domain. Then I have two terms that will be for the boundary condition, and at the end I have a last term in case of inverse problems that will represent the difference with the observations. Here you can see an example for 2D Helmholtz equations in the frequency domain. You can see there is a plot of the collocation points, so you define your collocation points over your domain. And what's interesting with neural networks, and you can apply automatic differentiation, so you can apply, for example, a Laplacian or apply your operator to the neural net. And this can give you the residual, this residual here. So this is the principles of the physics-informed neural networks. We take a simple feed-forward neural network. We can, with automatic differentiation, evaluate the boundary condition. We can evaluate the residual. We get it into the loss function, and we optimize, and we get an approximation to the solution. Comparison with traditional methods, what is interesting is that obviously there has been a lot of new techniques. So there are people who've been introducing, for example, the pins under a variational form. So you do not really need to use this kind of collocation method and so on. But it's a kind of summary of everything when we can see that in the case of finite element methods, it sounds like there is a kind of confusion here. Here I have the pins here. There is a problem with the basis function, but with the pins, you can use, in general, it's easier to use the GPU acceleration. You have the typical solvers. And in the case of finite element approximation, we solve the problem, as always, using conjugate gradient solvers or GMRS. So, challenges, and it's a discussion that is always emerging about all these communities, people who are using physics-informed neural networks, other people more from the traditional communities, from the FEM communities, saying that it's not working because there is no, in general, there is no convergence guarantees. So what's interesting here is to try to see how we can improve all these pins approaches. And generally, the big issue is about training. It's pretty hard to train this kind of models. So I will see like a few ideas that I've been applying to try to accelerate this training and try to have like better schemes. First, hyperparameters. Then we will see the data parallel acceleration and how to get the permanent regime. And finally, a discussion. It's not my work. There are a lot of work here at Inria Chile on loss balancing, so I will try to dive into this kind of ideas. First work, so it's pretty natural. We have physics-informed neural networks, and there is a storytelling with that. I started using them, the physics-informed neural networks, and it was not converging, and I was seeing that for some configuration, it was converging very well, generalizing, and then it was not working, so I started to try to use hyperparameter optimization, pretty classic one with Bayesian optimization, with Gaussian processes. There is a very simple implementation with scikit-opt, for example, and I tried to apply that to the Helmholtz problem. And what is interesting, so here we have the kind of classical hyperparameter optimization. You try to optimize your neural net, the configuration, the loss function, and you apply that to, for example, a Helmholtz problem. It's interesting to study the Helmholtz problem because there is all this wave number dependence, so with high oscillation. So that was a kind of simple operator, but that is not that easy to solve. And what can we see here? Here on the right, you see the convergence. So you apply your optimization, and over the iteration, you try to find the best configuration for the hyperparameters. And well, in this case, it's like over 100 iteration, and we see that like at 19 iteration, it starts like to converge to a pretty interesting solution. And here, it's not like the iteration, is the ranking. And what you see is over the 100 configuration, like the vast majority of configuration is not converging that well, but there are a few. In general, it's like around 5%, less than 5% configurations that are converging very well, generalizing very well. So that was what interested me in this study. And about the results here, it's not that easy to read, but you can see here you have the best losses with the best configurations, and you can see here that there are lots of configuration where the loss is not converging at all. There is no generalization, and it improves, and here you have like very good configurations. And in general, for these cases, what we could observe is that the quite shallow deep neural networks were giving good results. We could see that you do not need such a deep neural network in general, that it gives you like some ideas of the kind of loading rates that you can use, and the balances, the weights for the losses. In this case, it was a forward problem without time dependence, so there are just two components for the loss. We just could use pretty small weights for the boundary conditions. And you can see that also in this very vanilla case, training was deteriorating with the higher wave numbers. The tutorial, all the code, everything is available on DeepXD library, which is an open source library, very easy to use. So if you want to start playing with pins and so on, it's a very good idea maybe to go on those tutorials. Everything is available. And I'll keep on another example. So here, it's about all this data parallel acceleration, in about how you can scale your training, how you can scale your throughput with more data over more GPUs. So I've been working on that with also another joint work with Gonzalo Ruz from Adolfo Ibáñez. And we've been trying to see what was happening when we were trying to distribute the training points for the training. First, to get like not so much context, I don't want to dive into the theory, but what this theorem and result shows, people have been working a lot on how many collocation points, for example, or observation do I need to have a kind of permanent regime, so that I have enough training points. So it is a work by a researcher called Molinaro from ETH. I've been using this kind of bonds. And I don't want to get into the details, but what you can see here is that in general, you can get like bounds on the generalization error of your physics-informed neural networks based on one, here this is the training error. So the training error is something that you can control, that you know. and another term in general that is depending on the quadrature and the number of training points. So if you have enough training points, in general, you'll get like to a kind of constant that will be related with the training error that you know. So this is something that I found very interesting because here, for example, we take a very simple Laplace case and we try to observe how the training and validation error are changing with the number of collocation points that you are using. And you see that at the beginning, the training error here in orange is not is like the generalization, the validation error is here, and you see that it's not converging at all, it's not learning, and then you arrive at a kind of regime here, and in a few points more, you see that the training and validation error are with the same behavior. So in general, what we want when we are training these kind of schemes is to be here in this zone. And we don't want to be here. So the idea was to say, okay, in this case, I want to get to that zone. So I'll try to do weak scaling. For example, I start with 1 GPU, and I try to use more GPUs to get to that point. And in practical cases, it was working perfectly, actually, because here you can see the generalization without scaling. So I'm working with 1 GPU, and I will increase the training points. So I put more training points, and I see that I get to a validation error that is decreasing. And here I do the same thing, but I am using 1 GPU with the same amount of points, and I scale with more GPUs. So I have, for example, 16 collocation points, and I put 16 collocation points on another GPU, and so on and so on, and we see that we have the same kind of behavior. In the other case, when you do what is called strong scaling, is that you take a given amount of collocation points and you distribute them over GPUs, you see that again, you get similar convergence results. So weak scaling, strong scaling, everything is behaving pretty well. Over performance here on a pretty more complex case, which is the tutorial, like the introductory example from the RECI paper at the beginning of RECI and Karniadakis for Navier-Stokes. We do the same acceleration, and we see that in general it was behaving quite well. I was scaling from 1 to 8 GPUs, and I had an efficiency of 80% in this case. So here it could be interesting to try to get to more and more GPUs. I don't know, scale to 100 GPUs, for example, and see what's happening with the efficiency. Again, everything is available. I've added all this code to the DeepXD library, so you can feel free to play with the implementation. And well, to conclude and to finish, and about all this necessity of having more data sets, this semester I've been working with students from PUC, with Paula Aguirre, the professor, and they were trying to work on all this metadata. I need to make available data sets for this kind of models. How can I do that? How can I get good metadata of my simulation? How can I scale my simulation easily? And there is a whole infrastructure about that, because I can really attest on that generating good data sets in general is not that easy, and you need domain experts of the PDEs of this operator, and in general, there is no such availability of this kind of data sets. And well, to finish, and I will see if the video is working, but there is also a very interesting point about trying to compare fairly traditional methods and all these pins-based methods. So in this example, for example, here we have an Helmholtz problem with different layers. We are solving an inverse problem. So we do not know the medium here. We do not know the medium for a time domain problem. And we try to get a classical traditional adjoint method to try to see if it converges given observations. So here we'll see. I don't know if it's, no. I think I will not see the iteration, but you can see that it converges and it learns. So yeah, I think very interesting to compare these iterations. For the moment, we have the adjoint method, so the traditional method, and now we are finishing the implementation of pins, and we have like a real concrete comparison for a real case of convergence of number of iterations from your agent scheme versus number of epochs, for example, and try to compare the curves and the efficiencies. Well, to conclude, this talk was more about the pins, who in general are for few configurations. For example, you try to learn a single problem. Or you can add like more parameters, but this is more like a classical solver. But there are other like very powerful methods, such as all the operator learning class, which can be used to learn a whole kind of PDEs, to learn operators, and which is a very promising area, a lot of works, a lot of architectures, and we are currently working on trying to have like good data sets and to try to apply this kind of architecture to that. Thank you for your attention.
Thank you, Mario. Thank you very much, Paul. Do we have any question? Any question? Ginosa, let me.
Thank you very much, Paul, for the presentation. I just have a question. I don't know if it's a question, but like I see that you always have like the analytical solution of your problems. In case you don't have analytical solution, how do you learn your problem like for pins using pins?
Let me be. So, let me see if I understood your question. So we can. You are saying that when applying pins, we depart from an existing initial solution, no? So if we don't know the solution, I don't know. I am tempted to answer myself, but go ahead.
In case you do not know the boundary conditions, you're saying. Or initial conditions. In general, this kind of techniques can I don't know if I'm answering your question, but this kind of techniques can apply to all this. There is like with the unique continuation problem. So in general, people have been applying like these pins to cases where you do not know, for example, parts of the boundary conditions, so you do not know anything. In this case, it's just trying to adapt given observation, try to, like the kind of inverse problems, but where you do not know the, for example, initial conditions. I don't know if it's what you're asking.
I think that, just to give my own version, I think it's different, but this kind of, let's say, this case of problems, you assume that you have an existing model and you have data. There are different ways of them posing this. It's a direct problem, an inverse problem, data simulation problem, but in general, you depart from the fact that you have at least the model, no? Or you have the model and data. When I say data, it's like sensor-based in situ gathered data, no? And this is like the charm of this, that you make like two areas like reconciliate by models are not perfect by definition of model, and data is also not perfect because either you have a scarce data, and then data itself has noise and all of that, no? So, but it's like a priori assumption that you have at least the model to start with. Do you? Yeah. I mean, I'm just messing into. Any other question? Go ahead. Go ahead. No, you need to wait for.
Thanks for the presentation. I'm not really, have not studied so much the pins, but something that came to my mind was that in the example, at least, you were training with using a sinusoidal activation function. And so I was wondering if the result regarding the generalization error would depend on that choice, or is it independent, or what? Of the activation function that you use inside your network.
Ask me.
Yeah, I start and then you can complete. I'm not really, I'll be answering in some sense. Here, for example, this generalization result is not explaining what is going to happen with the training error. So in general, all what you're mentioning would go to this term. And a lot of people have been trying to get like more, like broader convergence bonds. And in general, you can prove that with a given kind of architecture, there exists a neural network that will be converging with what you want. But in general, you cannot like prove that any neural network is going to work as you expect.
Well, first in the morning, I think it was Francisco, or yes, it was Francisco. I don't remember exactly whom, but I do remember that he mentioned that he used hyperbolic tangent, no? And we have let's say, a convergent result to this. We applied some evolutionary algorithms to do like a sort of an auto-ML study of finding what is the optimal, the best activation function, and all different. This is what Paul was referring briefly at the beginning, and the result is hyperbolic tangent. So we applied, let's say, an optimization process to try to find, we have these other activations like ReLU and all of that are like the common choice. My intuition is that when you are doing let's say, the modeling part, that you have to compute these, let's say, complicated derivatives and all of that with the gradients, the hyperbolic tangent has like a smoother derivative, so it introduces less numerical issues in the let's say, in the system. Normally, like what in general neural networks currently people are using, like rectified linear ReLU, rectified linear U. I don't remember the U what it is. ReLU has this form of like two straight lines, so there is like a sort of gradient bump in the. It seems that this is a problem for pins, no? But I think one of the main problems of pins is that a lot of this is still to be discovered, no? Because we are messing with something that is also mathematically, like numerically complex. You see gradients going crazy and these things, and the neural network is harder to train. No? Sorry, I spoke about something I knew.
Yeah, and that's what happens always, because we saw that in the morning with Francisco. I had the same, they had the same, and it's about that, like all these methods, you can have very good surprises sometimes, you don't know why, and you have bad surprise in many cases. And well, you have to see when it can be a good idea to use this kind of methods compared to traditional method, when it always like works the same and you know that it works.
This is, by the way, there is an interesting side effect, is that if you have hyperbolic tangent, you cannot make really deep neural networks, because then you have the problem of vanishing gradient and all of that. So the rectified linear unit was like one of the ways of being able to do deep neural networks. So this is like, that is why this starts to get interesting, because you get, reality is creating you boundary conditions on the kind of things that you can do, because now it turns out that we cannot make deep, like typical deep learning networks, because the activation limits this. No, we have another problem that is called vanishing gradient. The term is a bit like catastrophic, but is that the gradients become zero if you add too many layers, and this is because the hyperbolic tangent. So I don't know, it's a fun place to be.
Yeah, thank you both.
There is one question, and then we need to go for the break for the coffee.
Hi, my name is Giovanni. Very nice talk. I'd like to add to the discussion that, well, since the activation functions are kind of a topic within this area of research, there are a kind of alternative to MLPs that was introduced this year that are Kolmogorov-Arnold networks that I think may be kind of useful in this context, because these networks replace each unit of a perceptron by a unit that learns a function that gives an output. And instead of having a perceptron that sums all the inputs, weights them, and applies an activation function, you learn a function per unit, and then you can get an output with very good results in several applications. It's a very hot topic right now, so I think that might be worth exploring within this context.
Yeah, totally. Actually, I've not been exploring and running there is, for example, a library. I was about all these GitHub repositories and so on, and there is all this fair comparison of PyCans and pins and all these kind of techniques. I know that all the results are available, so I just have to run them and see what happens.
Well, thank you very much. Do you want, please go ahead. No, please.
So, a short question. Is there any theoretical work on comparison between traditional methods and those based on the application of these physically informed neural networks?
In general, I do not have, like, in there are comparisons. I was telling you, in general, a lot of people have been working on trying to get showing, for example, that pins, or not even pins, that neural network can do the same as an HPFEM, for example. So you can show that there are kind of neural network that will act or behave as an HPFEM, and you can refine and you can get this kind of bonds. But it's just, you can show that you can find an infrastructure that is going to behave the same way. I do not have, like, more results. I know that it behaves very, very well with high dimensions, but, like, kind of fair comparison with, like, in general, there are not so many results, theoretical results of how it is going to behave. Or you have to be very restrictive on the class of functions or on the class of architectures that you are working on. I don't know, on one layer, for example, or you have, like, to simplify a lot. But I'm not aware of this kind of results. I don't know.
Why me? Well, I am not an expert, but like, from all the papers I read, which, by the way, this comes from the area of more mathematics, so they all rely on these results we have on multi-layer perceptrons, of the universal approximation property of perceptrons, that they can approximate any function with any epsilon degree of, like, I mean, not like that, given a function and an epsilon and some restrictions that I don't remember right now, there is a neural network that is able to approximate this function with that. And these are results from the 90s. There are more recent and more powerful ones, like 10 years ago, that I don't remember by heart now. But I know that, at least the paper I have read, they always start saying, okay, we can do this because there is this, no? And this is the, let's say, the theoretical foundation they rely on to work. That is the theoretical foundation of all neural networks, no? I call this deniable, plausible deniability, no? Everybody, when someone comes and tells me a neural network can solve this problem, yes, we have a theorem that says that there is a neural network that solves your problem. If I don't find it, that's another problem. But, the theory says that. See? Okay, well, so let's take a 20-minute break, and I return the baton.
Thank you. system challenges and opportunities for AI. Welcome, Pablo.
Well, it's a pleasure to be here. Thank you for the invitation to Inria Chile. And I will try to talk about a little bit about AI, but mostly about something very important, what is happening in the air system these days. And probably you have heard of it. And I just want to introduce some of the big challenges that we are facing, and in particular, something that has to do with tipping points, uncertainty, thresholds, which we are very used to it. I mean, we think that bad things will never happen, but it's just an insect flying through or moving one of those pieces of wood there could cause a sudden collapse. And this is very common in ecological systems and also in most complex systems that you can think of. In fact, there's this nice paper by Simon Levine and Bob May and Suji Gara on ecology for bunkers, where it shows up that the 2008 crisis of the banking system worldwide was part of what you would expect on systems that are complex and have all these nonlinear kind of interactions and might react sometimes with huge changes due to very small actions. So as I said, this is very common in ecology. In fact, since 1974, people like this guy, George Woodwell, in a kind of private assessment of ecological systems and the existence of thresholds, informed the government of the United States that there is a ecological system usually have thresholds, and those thresholds are difficult to forecast, and they can have bad consequences. And then back by 1978, the other landmark paper is by C.S. Holling, who became one of the major names associated to the word resilience. And he was the one who actually created the Resilience Alliance. And everything started with this paper talking about the resilience of ecological systems and its the stability. And resilience here was thought of as how fast the system can recover the equilibrium kind of state after being perturbed away from it. Since this paper, there was a huge literature on quantifying resilience, and new words emerged like robustness and resistance and so on and so forth. So all of this is just to mention that ecological systems, like very simple ones like a forest and an herbivore, could have or encapsulate huge surprises. And in this case, this is kind of well known. If you just look at the forest here, you can see these red kind of trees that are in the whole background here are dead trees because of this bark beetle here, who actually, the larvae, eats the needles, but also inhabits the bark along the tree trunk and cause all this damage, which is huge in the east coast of the United States and in Canada. And what we know is that there is a very simple model by Ludwig, Jones, and C.S. Holling, the same Holling I was telling you before, and is one of the first formal models that shows up in ecology, showing that there could be surprises, and usually this happens when you have, in this case, 3 equilibrium points. This is the death rate, and this is the reproduction rate of the budworm. And you can see that there's 3 intersections between these two kind of isoclines. And so the system usually stays either here or here, but it could be here in this unstable one. And eventually you can have these bifurcations in the system. And one of the major things is that you want to know is where the system is based on data, and to anticipate the way the system is traveling through the basin of attraction of the system. So in that case, what they show is that along this axis, if you increase the R, which is the growth rate, you go from A to B to C, and then you jump. And if you go from this way down, you go from D, C, B, and then you jump. So all those jumps are the ones that make life harder, because you want to anticipate them before they happen. And these things not only happen locally, like in this tree and badworm example, it can happen globally. And here is a time series. I mean, this is pretty much like remote sensing products that have been analyzed to quantify tree cover and mean annual precipitation. As you see that the system jumps from very low tree cover up to very high tree cover at around 2,000 millimeters. And those jumps are associated with the distribution of savanna ecosystems. So climate change will change those thresholds eventually, or make one of those thresholds more common than others. So you might shift, which is the case for the Amazon, eventually to going down. The Amazon probably is over here, and if you reduce temperature, or I mean, if you reduce precipitation, you might actually go into the other attractor, which is the savanna state, which will be disastrous for the whole planet. And the other example of this is what happened with the shallow lakes under the inclusion of phosphorus due to pollution. You eventually have a lake that is covered with vegetation, and if you increase the phosphorus, eventually goes down, and transition to one where there is no vegetation at all, and the system collapses, goes into a swamp kind of state. And the way down, which has been done experimentally, the path back to the system is longer, and it's different. A phenomenon that we call is hysteresis, which is very common and makes life even more complicated in the face of this system. There have been a lot of research on trying to understand how close you are to the tipping points. There are some hallmarks in terms of longer memories for the system. As you approach, you start fluctuating more, and the autocorrelation becomes larger. But still, it is an open question how far, or how to estimate how far we are from tipping. And this is very complicated because there is strong evidence that the biosphere as a whole might eventually shift. If this is the ecological state of the biosphere, as you go in time from 1700 to 2045, you will see that the number of people have increased, but also in dark green here is the amount of the land, of the total biosphere that has been transformed by human action. So theory predicts that by 2045, there will be strong changes all over the ecosystems, such that ecosystem services, or all the contributions that nature provides to people, will no longer percolate through the earth, but we humans will percolate. And that will be kind of complicated, because most of the flows that sustain the economy and sustain society and everything else will not be able to actually move through the planet. So what will happen, nobody knows, but certainly will be a different kind of biosphere. So anticipating early warnings and also trying to understand what will be the next state of the biosphere, those are open challenges. There are many groups in the world actually trying to do this, and probably a lot of them are in China, and trying to understand what would be like, or what would be the new world where we could actually go. And So this is one of the major things that I think artificial intelligence and all the different kind of approaches it encompasses can actually bring new insights into quantifying how far or how close to the critical transition are we, or the so-called early warnings. And this is particularly relevant for this, this system. This is the AMOC. It's called the Atlantic Meridional Overturning Circulation, which is a subsuperficial kind of a current that is warm in the tropical area, eventually goes up to the Arctic and Greenland, receive a lot of water inputs, and kind of frozen up, and all the water becomes ice, and all the salinity concentrates, goes down, and actually move back to the southern hemisphere. And in all those kind of paths, what it actually is doing is dissipating heat. And this is a major, this is called also the conveyor belt, but it's a major process in the biosphere, in the Earth system, responsible for a lot of what we see as climatic signal. Even it's been associated with acidity in the ocean, and also with a lot of what might happen in continental areas. The historical evidence shows that this system has collapsed many times in the past associated with glaciation events, and there is a risk that we might be close to a new collapse of this system. And this is one of the so-called tipping points in the biosphere. The tipping points in the biosphere for which there is data that they might go eventually through these transitions are not only the AMOC, but also the Amazon dieback, and so the boreal forest and tundra, the Greenland ice sheet, the Atlantic deep water formation, which is associated with the AMOC, and also the Sahara greening, the monsoon, and so on and so forth, and also what happened in the Antarctic, with especially with the southern oscillation. So the thing is that all these are part of the whole thing, you know, and when one of the system will collapse, the other will follow. And so now we have to understand not only one tipping point, but the interaction among tipping points. And that's really a complicated and really challenging task. And what I'm going to finish with this, which is an example of the complexities of the issue. And most models of this have predicted that the AMOC, the Atlantic Meridional Overturning Circulation, will last or will collapse eventually in 1,000 years from now, given the data we have and so on. But not too long ago, during the last year, there have been a kind of several articles in the main literature showing that the tipping point might be closer than what we expected, given that there have been a lot more data in the last 10 years on fluctuation in salinity and temperature across depth in the Atlantic Ocean. People is seeing that there might be symptoms of collapse of AMOCs, and one of the oceanographers says, you know, this explains that AMOC breakdown could be catastrophic both for human and marine life. So even if it's not that catastrophic, it's going to be a huge change. That's for sure. And it might impact economic systems, might create havoc everywhere. So it's something that we should care about. You know, this is one of my favorite slides because I usually, when I was a kid, well, wasn't a kid, but I was starting graduate school, I worked with stomach diagrams, which I thought it was so incredibly creative for a guy who actually do this, decompose signals in frequencies and intensities, and you can display all different kind of processes in a two-dimensional space. I was, oh, cool. I never heard of him anymore until we started doing some work with AMOC. And then I found out this paper, which is the one that actually inspired all the paper about AMOC. Back in 1961, he did these two vessels experiment. It's a thought experiment. And one is the Atlantic, the North Atlantic, another will be the South Atlantic part. And what he monitors is salinity and temperature. And he do the equation for this, and he shows back in 61 that the system has a critical point and a sharp transition and a tipping point. And he said, oh, this might actually eventually apply to some of the circulation we know in the Atlantic. Sure enough, it did, and people start doing a lot of deterministic models, as Stommel did, and later on, some stochastic models have showed up. And I'm fortunately enough to collaborate with a great stochastic person, who is Rolando Rebolledo and his team, and with Cristobal Quinao. And so we became interested in this because there were a lot of noise about that we might be close to a tipping point. So the question we asked, if we do the stochastic analysis, because most of the model has been deterministic, can we actually, is there any chance, can we quantify what is the chance that we might be close to a tipping point? And so we did the stochastic analysis, and then we found out that this was kind of pretty much done. Not in the way we did it, but, or asking the question we were trying to ask, but it was, and this, let me explain you briefly, this is just the salinity, and this is F of t is the freshwater forcing, which is the amount of fresh water that is melting from Greenland and the northern hemisphere. And this is the noise term, which is a Brownian, and the coefficient is given by this composite thing, which are two noise terms associated with independent and dependent impacts. So the big picture here is that the stochastic model predicts this, you know. This is the Brownian kind of a typical stochastic differential equation modeling, and this is the original kind of version of Stommel. This is the strength of the flow of the freshwater forcing, which might eventually cause the collapse, and this is the amount of warming that you might expect. So that system collapses at 4 degrees Celsius. That's home. You are here in a positive phase, and you go to a negative amok, and that's collapse, and the world we know it might be different. But if you, in this case, we change this to a stochastic version, and you see that the collapse can occur much early because there's always kind of some trajectories that go before the tipping point here. So that was interesting, and then we asked the question, well, are we actually modeling this the right way? Because most of the dynamics of temperature and precipitation, they have a very particular characteristic. They depend on many processes, each of which act at different time scales. And what is classical then is that the value that you are reading depends on many scales of things that have happened in the past at different scales. So it might have a long memory. And to model system with a long memory, you should not work with this Brownian, but with what is called a fractional Brownian motion. And the fractional Brownian motion was actually proposed by this guy, Hurst, who was an hydrologist that worked in the kind of flows of the Nile River to make reservoir for water, and he realized that, and he created the theory that was taken then up by Mandelbrot, and they kind of formalized it. And you can use it and do your stochastic kind of analysis using this fractional Brownian motion. When H has a particular value of 0.5, you get the Brownian, and where you are not in that regime, you can only do simulation because analytically it's intractable. That's a kind of a trade-off. But when we did this, you know, the Brownian. These two are Brownian, but this is when a little bit of noise increase, you'll see that trajectories can be more probable. And if you actually go into this regime of long memory, you see that the system either is here, or if you eventually jump into the other phase, you get stuck there for a long time because the system has memory and it's autocorrelation in time. So it's even more dangerous. And if you put warming into this system, as can be done, affecting the fresh water input, if you take the prediction for the end of the century of 4 degrees Celsius, between 3 and 4, you see that the trajectories, this line is 10% of the trajectories, actually predict that the collapse will be in less than 50 years. So the answer is yes, it is possible that the collapse can be close. It depends on the estimation of these noises, and the estimation of these noises and how close you are to a tipping point is something where eventually artificial intelligence could make a huge difference. I make my homework, and there is only one paper that I know of by a Chinese author who is in an archive on predicting tipping points. And so, two things. One is that, and I will conclude with this, is the importance of stochastic model with long memory to actually model the Earth systems and actually do policy based on those. And secondly, the need for having AI in helping to analyze time series salinity and temperature to derive estimate of these early warnings, especially since we have a very well known dynamical model for it. You know, so and AI can make a difference in order to estimate things and propose changes. Thank you very much.
Thank you. Other questions?
Nice to hear about the way that we're going to disappear very soon. This is nice with Pablo, that we always learn how we're going to disappear in a little time. So my question is, if you have a typing point that has not reversed, I mean, it's just a new issue that's going to happen, is another possibility that then you have another tipping point just to return back to your original state, in the sense that the phase change is reversible, but not this one?
Yeah. No, I mean, that's typically what happened. I mean, you go to a tipping point, and eventually, if the system recovers, it will go on through another tipping point back. And usually the way back is longer. So you don't jump at the same point again, you know, because of the non-linearities of the system, usually. And that's what has been seen. But if you do this fractional Brownian noise, it's even harder to go back to the original state, because since it is autocorrelated, it might take much longer for the system to go back to the initial state. So it's crazy.
Other questions?
Comments? I saw someone moving a hand. It was just involuntary movement. Okay, thank you very much.
Yes, I want to finish. So you do not have any prediction or about all these tipping points? You didn't do a prediction saying it's going to happen and going on press on that? You do not have any opinion on this possibility?
Well, this is the thing. I mean, it's like if you have a good model of the system, and you can do some of the calculations on how likely it is that this thing might eventually jump. My take is that stochastic models are very helpful in this situation if you use the correct noises, because the noise encapsulates everything that you don't know about the system that might affect it. So it's really great that the stochasticity builds in uncertainty in there, you know? So, and you can get a kind of a expectation of how likely something might be. Probably it's difficult to say when, but you can say, as the IPCC uses, you know, this is very likely that this might happen. And I think AMOC might be something very likely that might happen not far from now, maybe in 20, 30, or 50 years. Hopefully not. Hopefully we are completely wrong. So, thank you.
Yes, Luis.
Well, thanks, Pablo, for, as Adrián was saying, for rising the spirit. But what do we need to make these predictions better? Do we need a better model? Do we need a finer mesh? How can we help? I need to know exactly when I'm going to die, not...
Right. What I've seen is that, well, one of the things we need is to have a good understanding of the parameters of these models and a good estimation of them. There have been data, I think that's last 20 years on the Atlantic. People, I mean, there's these organizations that have deployed salinity, temperature measurements to understand this. And it might be eventually very interesting to see if we can improve parameter estimation and how those parameters change through space and time. That's one thing. And the other is developing methods that can actually analyze time series or the history of time series and being able to construct a way to predict jumps in the system. I don't know how to do that, but there are some deep learning tools, I guess, people have been using. And now, well, now that AI has exploded, there's a huge nomenclature of different SN, DD, SLE, S2 things, you know, and it's completely insane to trying to understand. But there is good, I think, attempts to pair models with, I mean, dynamical models with artificial intelligence.
I'm sorry if the question is too naive, but have these events happened in the past?
Yeah, several times, and there are good records in the past. Glaciation, for example, and the system collapses.
But no one was gathering data at that time. No one was gathering data.
No, right, exactly. Too bad.
Yeah, not that we know. Maybe the reptilians, you know. Thanks. I mean, it's a very interesting problem, and thank you.
Welcome. Thank you.
Thank you, Pablo. Well, our next and last speaker will be Adrián Palacios, doctor in neuroscience from Université Pierre et Marie Curie, professor at the Instituto de Neurociencia of Universidad Valparaíso, and the talk will be about the Retina and the era of big data. Adrián.
Okay, thank you very much for the invitation, and I'm going to try to return to life. This is one of the vision that is the subject of my talk today, is one biological solution to a physical problem that is just how to use the energy of photons to make sense of process. This is one picture here that show that illustrate one of the main results that was in 1800s or before the 1900s, I mean, is by Frank Ball that realized that when you stimulate one piece of the retina that is in the back of the eye, something changes. It's like an changing colors that goes from the purples here. Oops, let's see the. Okay, this is the retina that is just isolate from the eye, that change when the light is just on, that change color, and that was called bleaching. And from that time, people start to looking at what was this substance that changed in color, and then they call this rhodopsins. And the rhodopsins is one part of the protein that is in the eye that is combined by another element that is called chromophore, that is an aldehyde of the vitamin A, and that these both together make a visual pigment. And the visual pigment is the substance and the component of one substance that make possible that you interact with energy and you interact with biology, and that is the start of the visual system process. And then after years was the work done by psychophysics in the United States that they were like looking at the level of the threshold where the perception of light in humans start. And that was done in very careful experiment where people were showing like a small amount of photon that increasing in amount, and they detect when the human being is able to say, okay, I'm seeing something. And that was one very nice job done, because I mean they show that the visual system in the level of the human perception need a very small amount of photon just to react. And then was in the 80s, that was the first time that in the labs, this was in Stanford with the Baylor labs, where they were introducing a very nice technique that was, this is an isolated retina with 4 receptors here. It's like 40 microns and 10 microns in diameter. And this is like a suction pipette. This is a glass pipette where by suction you can just introduce the auto segment of 4 receptors, that is the device that catch photons inside of the pipette, and then creating like an electrical resistor here. You can measure, when you use light, you can measure the activity of the one single 4 receptors. This was the first time that we are really facing the sensitivity at the level of the one single 4 receptor. And then was a very nice paper also by the 60s with Francisco Maturanas here, where they show was at the time in MIT, or Harvard, that they show that actually the frog retina, the eye of the frog, were able to respond to movement. So there was a little bit more complex, not only detecting light, but also that the structure of the retina was able just to detect or combine signal to create the capability of response to movement and orientation. And then the talk today, I want to try to make sense of the long history of the visual system, trying to put what are the challenges that we are facing in the lab today when we are now able just to record it for thousands of neurons at the same time. So here is what I want to try to follow today in the sequence. And the idea is that this is something that we do in the lab. We think that is very important, just to make that every time that you study like a sensory system, you are trying to understand the evolution of this system, the natural history of this organ or sensory system, coupled with the question that your place where you are evolving is also have some property, like the physical property of the land or the air or the water where you live. So we are always thinking about this solution, about the biological solution need to respond to some stress that come from your own land or air ecology. And here is some numbers. I mean, what exactly the retina is in terms of the number is, in the human, we have like 120 million of photoreceptors. This is in the end, I mean, in the beginning of the retina, but the output of the retina is like 1.5 million of ganglion cells that are the ones that are responding and sending their response to the brain. So here we have a huge problem. I mean, how we reduce this 120 millions in 1.5 million. You know? This is, we start already to understand a little bit the complexity that we are facing in the lab when we are trying to understand how the retina is connected to the brain and what the retina is sending to the brain for create perception and the way that we interact with the world. And this is also numbers about what is important for us, also about the energy, the way that also the retina face disease, and also is a very good biomarker for Alzheimer's or other pathology that affect the eye. The retina is one part of the brain. I mean, it's something that has the same nature that the brain, say the same kind of the synapses and the neurotransmitters. And then this is like our loop in the lab. We are collecting like samples from organisms that live in some ecological system. We go to the lab, we study functions, say we're using like light just to create and like to reproduce what they are facing in the real life. And then we create a lot of tools, you know, that goes from to trying to understand what are their capability, how they respond to light, if they are like a nocturnal, diurnal animal, so on. This is the eye here that I'm showing here. This is all of the dioptric of the eye. It's an optic system that creates like projection of one image in the end of the eye, where the retina is here. This is a retina. I mean, it's like a transparent tissue, and here is a high reproduction. I mean, high electronical image where we see the photoreceptor here. This is like rod here, and here is like cones, and there are very, I mean, tiny, tiny cells here that are here in the retina. When we see the retina like layers, I mean, and several layers here. Here is the layer of photoreceptor. Here we have a synapses. That means this continuity of the network where there are many different type of cell. This is like horizontal cell, bipolar cell. Here you have amacrine cell, and here is the output of the retina. That is, there are ganglion cells. These ganglion cells are like collecting signals to send this to the brain. And here inside of the photoreceptor we have like a very nice mechanism, biophysical mechanism that are sensing, I mean, the amount of energy that coming from photons, and then create like an electronic exchange between sodium and potassium here, and this is called a dark photocurrent that is like sensing this amount here, and then sending this like transducing this like a signal that is, I mean, sending to the first synapses in the retina. So this is a very nice system that is in place from, I mean, years and years. And we in the lab, what we are doing is like we are using in the last 10 years, I would say, this small matrix of electrode. This is like electrode that are here separated by 100, can be less or more microns between them. So this is we put here an isolated retina in 1.5 or 2 by 2 millimeters square with plenty of electrode, 256, and today we have also with 4,000 electrode. This is our lab, and here is that. So here is one channel, I mean, one electrode here showing this is very sparky signal that are spike from the retina, from the ganglion cell, and this is 254 electrodes sensing in the same time hundreds of neurons that come from the eye. You see, we just present light like an stimuli, and we record the end of this retina, just trying to put ourselves in the level where the retina send signals, massive population signal to the brain. And here's like just an idea about what is there. After we process the data, we obtain this kind of the raster. Here is time, here is number of 20 cells, just an example. And each time that we see this small mark here is one spike that was sent or created to be sent to the brain. And this is an example of see what we do with data. When we just present like white noise, we can just recover some property of this ganglion cell, like where physically they are in the retina, which kind of just to know which kind of the signal they receive, just to create the response that we are observing. Essentially, the retina also is, have the capability to create, like, from mostly to the first synapses, can create two kinds of the signal. One is on and one is off. That means that I want to be excited by light, or I want to be, I want to be in silence. I want to be like a hyper polarity, or going to be like a signal that's going to send signal or going to suppress signal. And this is the way that the retina is working, like, just with the light on or light off, in the sense that it's like a switch and balance between the signals. And that is created by several molecular receptor, that is mGluR6 or 1-pakinate, a glycine, that make like the teeny changes between this network, just to create a more fine-tuning response to several patterns of light. And here's one example of what we do in the lab. Is just using like this kind of the stimulus, like light on, and then a frequency that's increasing in time and in intensity. We look at here is 10 repetition, 1 cells. We call and raster this in time, and this each time that we see this kind of the mark here is one action potential. That means that we create. When we repeat and stimulate, each ganglion cell is creating like an on pattern that is not always the same, what we see here, but is created like their own solution to depending on the state of the network. And this is just what we call the post-stimulus time histogram, is the accumulation of this spike in time. And this is the stimulus. So with this bone, just to show that all of the cells have their own way to respond to the same stimulus. That means we have a diversity of the response depending on the type of the cell. That make an idea that we are not facing like a camera, a photo camera, but something that is much more sophisticated. And just to let you have your imagination here is that the way that we are in the end of the eye, if we just, this is unreal, data, is just put this in a way that we are like flashing in one of each of these, like a spherical shape is like one one ganglion cell that is connected there, and each time is not all of the cells respond to light with the full stimuli here. But it's like a group of the cell that is responding. And this is what your brain is facing always when you are looking outside of the world. The visual stimulus is creating patterns of light that are, the response that are sent to the brain, and the brain need to read that. Need to make sense of this, like a statistics, way to process one entry that is light. So the first, point here is that the eye is not a camera, it's not sending any image to the brain, but it's sending like a way to code, to neural code, what is in the enter. And let now just to move a little bit about what we do with all of this kind of the result that we obtain in the lab. And it's true that we have, in the one way, I mean, is we can study like the biophysical law of the synapses, I mean, how they work in terms of their own electronics. Inside, like, is charge, I mean, ions that are positive or negative, inside, outside of your neurons or your elements in the network. And that is one way that we have been working in the past for many, many years, trying to make very knowledge, I mean, just to have a very knowledge amount of data and just to try to interpret the data in base of the very simple connectivity. But today, the idea is that in face of the new technology, has been a very, I mean, we have been switching the way that we understand our visual system, our brain as well, in function of the paradigm that has been started very early in time. And by the 50s, was a very nice work by David Marr that was one of the first just to put the visual system in the context of computational level. This is a very nice work, book by him. He was dying very young, but they put really the fundamental piece that the retina and the visual system was a system that has levels, level of computational level, algorithmical levels, and also an implementation level. And that was essentially today by biology is that, okay, what the retina is doing, I mean, in terms of the process the light, then what is the computing is kind of the algorithm that just using all of this response of the neuron to create a little bit more sophisticated response. And then also what are the structure of the retina, and that is something more like the anatomy or the, I mean, the genes or the protein that are there. From that time, I just put this like what we are trying to do in the lab, I mean, like a pipeline. We are having like retina register, I mean, we're just recording from cells with this array of multi-electrode. We also are phase of that we need to do like that data pre-processing, like noise filtering. We need to make all of this feature extraction, normalization. We also need, this is very important, where we save, you know, when you are using this for 1,000 electron matrix, we are facing with half of terabyte by experiment, or gigabyte if we use a small one. So this is something that we are very, very concerned about that. And by the other side of the process is also all of this question about interpretation, visualization, machine learning analysis, and then we are today using models like supervised model and unsupervised, also time series analysis or other kind of the neural activity based models. And also in the lab we are working with several transgenic mice that are more like model of Alzheimer or Parkinson, essentially Alzheimer, where we are trying to understand what are the like early signals that are happen at the level of this retinal network, just to predict if something going to happen in the future. And also with some gene therapy, we are trying to just to help that to the follow-up of this change in the retina. This is one example of the data that we are collecting in the lab. This is one from Octodon Daewoo. This is a rodent from Chile. That's when you keep this in the lab, it can live like 10 years old. I mean, a very old rodent. Normally in the wild, I mean, their expectancy of life is just 1 or 2 years, no more. And just to mention that we are interested in this, what we call clustering. And for clustering is, I mean, it's a methodology that maybe most of the people know today, and it's just to make sense of what we can just collect from the data, just to collapse the different neurons in a similar class. It's an exercise of how we use group cells that apparently they are not in the same group. And for that, we use our data. Like I said before, we collect with several kinds of the stimulus, and just to go to the several paths in this kind of the algorithm that separate the neurons in one level, one after the other. And this is one of the kind of the results that we're using today. That's what I say, just is one example of that using this cluster. Here is an example of more than 7,000 neurons that we are just putting in this in the clustering model, and just sometimes we use kind of the feature that we extract from the time series, is what we call a spike series, and we can use either like autoencoders or similar clustering, or use the time series of the spike just to create the clustering. And the idea is just to separate different families of the response just by grouping them and trying using that like to make prediction about the aging, neurodegeneration process, and so on. This is one of the applications that we are working in the lab. So has like a part that is more like trying to understand how this visual system can be a very good or not biomarkers, just to predict the evolution of some change in the network that is related to age or neurodegeneration. The story here that is a big problem, because the diversity in the retina is the rule. That means that we are not having like one single cell that connected with another kind of the single cells, but it's more like a layer of expanding number of cells, like 1 or 2 in the beginning. Then we have at the level of the first synapses, like 10, 12 different kind of the bipolar cells, and then this like connecting cells that are amacrine cell, also there are like 20 more, and then we go to the ganglion cell that we have been describing like 20 or 25 different types of ganglion cells. And from this data, so we are now trying to go the data that we have can be now being used. We have not been used ourselves, but I predict that this can be used to create better brain-computer interfaces, or just to use, this is something that we have been collaborated with some robotic solution to autonomous vehicles, medical imaging, and also some, augmented reality, that also our data can be used for that. And that's the idea, is that this is one kind of the conclusion of what we are doing, and other lab as well, is that in the end, it's like having like video camera that has like 20 different channels with their own properties that are sending to the brain. It's not just one picture that you just take and send to your brain to do the brain trying to compute that, but it's more like a 20 or 25 or a little more sometimes. This is the complexity that the brains need to solve. So in that sense, it's like a nice solutions to this problem of energy, of light, but with some particularly very sophisticated way to do that, And we believe that this can be a very nice way just to go to improving what I said before, brain-computer interface and so on in the list. And just to have some kind of the wrap-up conclusion is that the field need today this interdisciplinary collaboration. This is very important, just to collaborate with engineers and biologists and genetics and AI and so on. And also try to understand if the scalability of the AI model can be also applied to this, massive way of having data. And also if what's going to be also solution, this can be applied also to use this data just to go to more like apply medicine, to create a very good way to create biomarkers. This all as well this main challenge that is very important, has all field of the IA in terms of the neuroscience is a big compound. I mean, it's a very nice, I mean, one of the best, I feeling that is one of the best place in the science, just to when you are facing to understand how your brain is working. Has some very good complementary work with AI. Also understand the way that we are interact with the world in the general sense. Also is a very good way to go to understand what is cognition, that has a lot of application in education and health. And also, this is very important also, is the one we are just creating this like neuroprosthetics or brain-computer interface, go deeply. The need is just to go to this privacy concern and ethical issues that is so important today, that we are not just creating new interfaces, but also what we are creating this interface. I mean, what are the implications for the ethics and who will be using them? You know? And okay, this is people that work in the lab. So all of Bruno Cesacti, Villa, Frédéric Alexandre come from the INRIA, and also we are having funding from Fondesit and also from the Air Force in United States. So thank you very much for your passion.
Thank you. Questions?
What a surprise.
Visionary talk. So, Adrián, I was wondering if you change the sequence of excitation, you see different responses. In other words, does the order of the excitation matters for the response? Meaning, it is maybe is it commutative or is non-commutative? The
this is a very nice, topics in the sense that this is like a machine that is built in a different state. Yeah, you starting one state is like your first stimulation, and this is at the level of individual ganglion cells that are in the output has a response, and then everything change backward, and then you really have the same, you present again the same stimulus, exactly the same, and you have a kind of a different twist to the response. So if you would like just to understand how this machine is built, really we need to do is just to look at the distribution of all of the possibilities that you have in the end, to understand the way that your network is just switching gears, each time. So this is very complicated because it's not one response always in the same time. It's one probability of the response, knowing your and distribution of the possible response. So no one has been really grabbed this tuning. People normally what they do is just average, and that is a very bad way to do, but it's the way that people have been working today. With Rolando Rebolledo, that you know, and one of her students she's doing that. Trying to understand from the level of the single response, then the next one, and the next one, how many states you have. And the problem in that is a population problem, because you have 300, 400 neurons at the same time. Each one is doing his own switching a little bit. So it's a very beautiful model. So.
Thank you.
Thank you. I'm afraid with the time we have, we'll go for no further question. Thank you for your talk.
So, we will continue with the roundtable, Science in the Era of AI. Welcome to the stage, a Luis Martí, Kartik Alahari, Paula Joffre, Pablo Marquet, and Adrián Palacios. Welcome.
Hello. So, well, thanks for. We are finalizing this afternoon session with this roundtable. After the good news of Pablo, we know that all AI we are doing has no sense, thanks to Adrián, that we know that we are capturing 1% of what the brain does. But I think this. We always talk about this, that machine learning needs to revisit the biological basis of cognition, because there is a lot of interesting stuff we are missing. But let's talk about how AI is actually changing how, not only, let's say, the scientific results, but how we do science in general, no? So I have some questions that I prepared, and curiously, I don't fully remember them. Okay, so the first one is for each one of you is how are you perceiving the impact of AI in your work or the people around you? So let's do it, let's say, in the short sense we have been seated. So Kartik.
So I think your question was about the impact of AI in our fields. So maybe I'll turn it slightly differently and say, is there anything in the field? So I work in computer vision and topics related to machine learning. So I would say, is there anything that has not been impacted by AI at all? Because in these topics, almost every single problem going from, let's say, image segmentation to object detection to understanding scenes, every aspect has been, touched upon by the latest developments in AI, including, the wave of deep learning methods, and now the large language or large multimodal systems. So everything has been impacted in a good way, because there's been a huge improvement in performance that we have seen, but which has also made people to kind of use these techniques in real products. We don't see autonomous cars everywhere, but you do see some services, especially in the US, like Waymo, for example, who have these autonomous driving systems where a car comes up to your house, picks you up, and drops you off at your destination. So, and that is run by mainly the latest methods in AI. So on maybe the downside of things has been that some of the core fundamental concepts that exist in computer vision have sort of been forgotten, because there are things that we can do without using any of the latest AI techniques. So maybe AI has become sort of like a hammer that people have taken.
Stick, that we hit everything with.
Yeah, especially also, you can use the hammer for the same hammer for everything, but when you don't need it, why go all the way? So I would say there has been a huge positive impact, but it has come with, other disadvantages, which I guess we'll cover in the later questions. So.
Sure, Paula.
Yeah, I was thinking to complement with, of course, when we do research, of course, on one hand, what is evident about AI is probably the way we are dealing with this avalanche of data that all the fields are facing, that there's more data coming than what we can analyze with classical or with traditional methods. But I also think that one part of science that is, where I see that AI is really having an impact that I don't really know how to handle at the moment is is the way we teach, right? Like science also has a lot to deal with how we propagate the knowledge to the younger generations, and it's kind of difficult to give them a book because books are getting outdated very quickly. Internet is moving so fast, and and the search machines and ChatGPT and all the way that you come up with making yourself an opinion or informing yourself about a specific topic on the internet is sometimes much more efficient than even taking kind of a course on something. So I think that there is also kind of a huge impact on AI in the way we do science, but in the way also we teach the science. Coming back to the fundamentals, yeah, like, classical method going through, in the case of physics, solving the equations and understanding it by reading a lot of books and taking the time. AI has accelerated in a way the things so much that it is getting sometimes quite difficult to really teach the next generation in how to do things and teach them something because they can learn a lot of the stuff when they look on the internet. So it's probably also about, not about the information, but about how do we, I don't know, navigate in this information in an efficient way. So.
It's a very good point because we need to learn to use this. It's still like too new for people to fully adopt it. Pablo.
Thank you. I agree completely with that, what you guys have said. And let me explain a little bit. I mean, somehow all these methods and artificial intelligence methods and so on and so forth have come to the rescue of the huge amount of information we were facing, and it became more and more difficult for us to make sense of it because there are more people in the world doing science, there are more journals, and it's difficult to be up front or up with all the new knowledge that is being generated. So as a tool, it's fantastic. So it's like we are going through a new acceleration of everything we do because it's impacting everything. And that's wonderful, but it's terrible too, because we do a lot of bad stuff too. So I don't know if you guys have gone into these sites of a particular site where people publish all the retractions, which is called Retraction Watch. Retraction Watch monitors all the papers who have been retracted from the main literature because they were fraudulent or the data wasn't clear enough of some other problem. So I would say, and I can bet on that, that in 10 years, this thing will actually skyrocket. Because, or maybe not, because now we're going to be so smart that you can publish crap and nobody will eventually find out because artificial intelligence will allow you to actually make fake things pass for real things too. And it will, so the message is that it will amplify everything that we do right and will amplify everything that we do wrong. And in terms of environmental impact, the same. I mean, if your business is to extract oil from shales or gas from, all these deposits, probably with artificial intelligence, you are going to speed up the process and you can make more money in less time. And we all know the consequences of that. So it can also help to preserve and conserve biodiversity. And we already do that a lot with AI, but it can also serve the wrong side of the force, so to speak. That's one thing, and the other are the epistemological consequences of this, which is that we become too dependent on data and phenomenology and phenomenological models, and less so on emphasis on developing first principle theories about the world. So I think that both things have to go in tandem, otherwise we can get people say that is the sense that we understand, but we don't. You know? And the last thing that impact that it has is if you start creating all these pipelines using artificial intelligence, there is the risk, as people have said, of creating scientific monocultures, where you reduce diversity and point of view because you start doing everything is standardized and because it's suited to the model that you are using. So that's also complicated.
Hello. It's working. Yeah. Okay. My feeling is this in this area. I come from neuroscience. That we are teaching neuroscience in different levels, and also in the university. And at least in Chile, it has been a slow, I think, absorption of what exactly means artificial intelligence. In the sense, this is not something very. I mean, it's not new. You know, when you follow this history of the trying to understand the brain and then the computer science and so on, robotics, this has been there for a long time. So what we call, my feeling today here in Chile, artificial intelligence, I'm not sure exactly what are the definition really is the way that you are using the ChatGPT. I see this is very, I mean, it's like a nice calculators and help a lot of, you can write maybe letters and the students use these, sometimes they don't cite, so we have kind of the trouble in the evaluation because you don't know exactly what is the use of that. That is like that. But I feel that when we are calling to pronounce ourselves about artificial intelligence, is a little more deep use of that. And that is, there are very nice areas like understand the structure of the proteins. And that has been a very tremendous, result. In the last year, we have learned about thousands of the proteins, the structures. I mean, the model that just create the structure, and that is a big issue. I mean, because this is an accelerator of all of the use that you can think about. Pharmaceutical uses, use it for therapy and so on. So this is something that I like much. The other, use for education. I'm not really sure that it is helping a lot to our brain. You know, just to use our brain in a better way, because it's like a substitute. You know, you make more in less time, but you are not using really your brain to create knowledge. So I'm a little bit more like in that part of the discussion, you know, about is the use of what you are thinking today, that is the use of intelligent artificial, that I don't think is really the only, ChatGPT is not the only way to do that. So my reflection is in that level.
Yeah, I don't know. I think that first, for example, listening to Pablo, this is something that where I personally feel that AI can help my work. No, there is this overwhelming, increasing amount of papers. Yesterday we were talking of a project we had during COVID related to understanding papers that were produced, and we had this exponential increase of papers available. Even now, even more now that we have this culture of sharing papers freely on archive or bioarchive or different ways, which is great in a sense because you have like early access, but then this is also not peer reviewed, so anyone can upload anything and you can generate a whole big fuss. And we are seeing that in the AI side, that these big companies release these reports and they can get a lot of attention. Actually, the report says nothing. It's like, the GPT-4 report looks like what's generated by GPT-4. You know, it has but it's very important if we can turn this into a tool, no, that allow us to, let's say, first on understand information more efficiently and probably use AI as a minion that you can see the idea and see what comes out later on, no? I don't know.
So maybe just on this point, actually, I just wanted to add, so it's true that there are tools that are doing this, and it's, I guess, at the beginning of the big effort that we need to make. So a couple of examples that I heard of recently, one actually from the US, maybe a smaller initiative called, as maybe some of you have heard, it's called Aurora GPT, where the idea is to create, or they created a model which was trained on scientific publications to be able to then query the model to get maybe useful information. And a similar initiative was also done recently in the past couple of years in South Korea. It was called KONI by an institute called KISTI, and they also have a similar initiative where they took huge quantities of scientific publications and they created this model. So it's a model based on, you know, the large language model we heard about, for example, from Meta, like the llama-based model, but they trained it or fine-tuned this model on this huge quantities of scientific publications to be able to then query this model, you know, with useful information and potentially maybe create resumes of articles that are published. But maybe a warning here is, you know, they do use maybe lots of data from archive and other archiving tools which have, as you said, you know, non-peer-reviewed tech reports essentially. So there could be, you know, a lot of noise in it, but maybe this is one way, as you said, to, so the way I see it is to maybe, you know, it's hard to do a literature survey these days. So maybe make this problem easier for researchers, for us, so that we can, you know, look at more difficult tasks and let the you know, simpler tasks be handled by, you know, tools that we can create maybe.
Yes, I mean, just as an anecdote, a couple of months ago I had a problem that I didn't know how to solve. So I got frustrated. I mean, you know, like today was a Friday afternoon and opened ChatGPT and said, please provide me some options to address this problem. And well, you know, generated, you know, ChatGPT is like a politician. It's very certain of what it's talking about, but knows nothing, no? And so it provides me, you have to do this and that. I say, no, please, give me references. So for every item, generated a list of papers that I need to read from archive, all fake. No? The link actually worked, but linked you to another paper that had nothing to do. So, but the direction is correct. No, I don't know. For me, maybe I am too positive, but of course has a lot of ways of misusing everything, like everything we invent, by the way. But also there is a, I don't know, a positive way, positive issues. Talking about bad things, what risks or negative things are you feeling or you think could happen in each of the fields of work in which you are working of AI? It's a little question, you know. But
little question maybe, but with big impact. So one of the things, right, that is happening, maybe I'll take a point of view from the peer review process of scientific publications or scientific, you know, submissions that we make to conferences and journals. So we are seeing, you know, different things, issues have come up where some papers have been generated using some of these popular tools, and I think it's gone to the extreme case where there was a paper that was submitted with, you know, a warning that you get with ChatGPT said, oh, this is generated with ChatGPT, what everything I say may not be correct. So there is a warning that usually is being added to ChatGPT and other tools. And there was a publication which was submitted to some journal, not the best ones, but still a journal, which is archived, you know. And it had this warning, it was accepted, published in the journal, and so it's essentially archived. So which means the process has completely failed. You know, the editors who handled the paper, the reviewers who handled the paper, none of them actually were able to signal this major issue. And similarly, on the other side, so this was a problem with authors, but there are also problems with reviewers who, you know, are not supposed to use these tools to create reviews. but there have been several cases, I think in several major conferences, where people have found that some reviewers have misused these tools to generate reviews. So that is a huge risk, where papers are generated by models and reviews are generated by models, and there have been even cases where area chairs, the people who are part of the program committee, have also summarized the reviews using these tools. So there is misuse of this power that we have these models at different levels. But on the other side, to maybe take a positive spin, maybe some of you have submitted to ICLR, one of the major machine learning conferences for next year, 2025, where they did a smart thing where they integrated one of these tools into the reviewing system, where this is for the reviewers. When they write a review saying that, oh, this is all completely not novel, some people have done it, but then if the reviewer does not justify with references saying, oh, it has been done in these examples, then apparently this tool will prompt the reviewer to say, hey, go back and correct your review because you haven't given a review that can be justified. So there is also some positive things maybe that will come out. So this is one first step that was taken, earlier this year. So maybe there would be more.
Thanks. I always say that eventually we will have like a dimension expanding process in which we provide a sentence to AI, produces a paper, this paper goes and the reviewer turns again to one sentence, read it and say, okay, and it's AI talking to AI, So it's a joke, but we have this thing of automatic, everybody's trying to automate the work, so maybe we just need to sit and talk, not write papers anymore, I don't know. Paula.
That's indeed very, very, I think that a lot of scientists are already doing exactly that. Like, why should I bother? I think that the problem is that everything is getting very accelerated, and it comes back to what you said, Adrián, about using the brain. I think that in science, if we stick to this, we're providing new knowledge, and I think that, a fundamental task of it is us humans using our brain for it. So AI should still be a tool that should help us to do most of this mechanical stuff, maybe more efficient, but we should always be very, very attentive of not losing our ability to think. I'm slightly concerned by the newer generations would not write a code themselves because they can just ask ChatGPT or anything to generate the first code and then do it, and then, oh, they want to do this a little bit better, so then they have all the other stuff and copy paste until you have the nice plot in the way you like it. But there is a mental process in how you make the first code that sticks in your head and helps you to bring some level of logic of the process and some critical thinking about the process. So it's very difficult if you don't make this exercise, then how to evaluate a work, the novelty of it, or if it's making sense, the discussion, when you don't have that thing in your brain kind of incorporated somehow. So I find this slightly concerning because you see with the newer generations, we tend to believe so much what AI is doing for us, and sometimes when you analyze something in a very classical, stupid way, with all the big uncertainties and the inefficiency of it because it takes forever and you cannot do it for a large data set or whatever, and it looks stupid and old-fashioned, but there is a process in it that you understand what is involved, that when you put it in a machinery and then after 5 minutes you get a beautiful distribution, you lose that. And I don't know if this is important or not to know. I still believe that it's important to know. So I am not very prepared to give away and say, yeah, do we know it or not? But so yeah, I think that we're in a moment of transformation in which people would say, do you need to know the shape of the cow? Do you need to know which part of the cow when you buy a steak in the supermarket? Do you need to know that or not? Maybe we don't, I don't know. So I think that, do you need to know all these steps? I'm not sure whether the answer is yes or no, but I think that there is a risk there of losing some ability of critically think about the scientific method and the scientific process when we automatize so much and we let so much AI kind of help us. Yeah.
There is something we are going on. So, as I mentioned, I mean, most of the wrong things will be the same things we do now, but we will do it in steroids, you know, much larger scale. And but there are the subtle ones that eventually can have an impact the way we think, the way we perform in society, and so on and so forth. But one of the good sides of, well, AI has this positive feedback because it will allow us to publish more, and then we will become more dependent on having the tools to make sense of what we publish, and so on and so forth. So, and then we will kind of miss having human qualities around. You know, it's like probably for the new generations, I mean, people will not be concerned much about how many papers or something like that, or the impact factor, but about how you perform. If I talk to you and tell you, go to the blackboard and explain me this formula or this calculation of that. You know, it's like, or talk to me about what are the things that you are doing, you know, which is something going against all these thing about beat counting, which is mostly the evaluation that we get in our institutions, because there are so many people around that you cannot have this luxury of, or maybe they will actually have an AI agent doing the exam. Probably, I don't know, but it's complicated. It's difficult to figure out what's going to happen. But I think that the good side of it is that we will value creativity more, and overall, the art of asking the right question. So, and then having the brain to interpret it, the result, whatever.
Hello. Yeah, my reflection on this question is, I want to separate this in several small words. For productivity, is very nice. I mean, you have nice productivity process that are having a lot of benefits for artificial intelligence help. Then people more like mature, like me, and that I'm very, thinking about what I'm doing. This is also very nice because last week I was like putting like in this ChatGPT a matrix with 10,000 lines and 24, I don't know, variables, and asking questions about that, and that is fantastic. No? Also for the disease, like creating this interface with people that have disability, this is also very nice. But the part that I'm not very, that I don't like much is that we are losing capability, mental capability. We lose a lot of memory with the use of phones. The iPhone, we don't remember anymore our telephones, phone, from people that are very close. Then we lose all of our capability also to orientate ourselves in the space, like with the GPS. So all of this, we are being now less human being in that sense. Now the problem is that what happened with the young people that start, you just start to using this from the beginning. That I don't know what's going to happen there. You're going to be in the end by something that is not really the use of your brain in your all possibility. And that I'm afraid of that. That is true. This is my problem, that I'm really afraid what's going to happen. Also, I changed the domain. It's not good for citation, like you said before. That is very biased. But this is something that's going to change. That is I mean, in the future, we're going to have very good way just to reference in this ChatGPT. So I don't think it's going to be a problem. But I'm more concerned about this aspect, the human being. You know, how you're going to be connect to this new tool that help you a lot of, but also prevent you to use your own capability to do new things, you know, just to think. Use your brain, all of your magnificent possibility, and this is something that I am a little bit concerned.
Yeah, well, thanks. You reminded me, a while ago I was listening to some podcast to fall asleep, and they were talking about this impact of technology and how the U.S. Army stopped training the soldiers using GPS devices to orient themselves in the field, because they discovered that the soldiers lost a lot of problem-solving capacities of spatial orientation and know where to go, because where they trained that capacity moving in the field, no? So by using GPS, they were only looking at the GPS, so they didn't train that part of the brain, no? And they decided that they remove all GPS devices and they just use map and compass to navigate the terrain and all of that. Not for the task, because for what they learn doing that task, no? And this is very common to all tools, no? So, not only AI, by the way. You just mentioned a couple that are new technologies, no? I am trying not to have a lot of opinions, but I do. So yeah, just to wrap this up in a more, let's say, positive key, what things would you ask this, let's say, ideal AI? We are in an AI-focused conference or meeting. What would you ask for a good AI that could help each one of you either addressing particular problems or behaving in a specific way? What would it be?
Yes, I think.
So we are taking notes and
we'll do all that.
Asking ChatGPT to create project proposals. So speak clearly.
Exactly. I think we already touched upon this a little bit. So, which is to maybe have AI models that we can trust to do the easier or the tasks that are very mundane, maybe cumbersome, tiring to do, but something that we know, like for example, summarizing the literature or a particular topic, finding all the relevant stuff that exists. Sure, then there is the next step. I think I like to acknowledge what Paula also said in terms of critical thinking. Maybe to contradict slightly what Adrián was saying about, sure, with the evolution of technologies, we have lost certain capabilities. Like when I grew up, when I was much younger, there was no cell phone. So I remembered my home phone number, as you said, my parents' phone numbers. Now I pretty much don't. Only the phone numbers that they used to have maybe 30 years ago, which have changed. But then I feel like, okay, maybe that's okay to kind of delegate this task. But what I think is important that Paula was also saying is to not lose the capacity of critical thinking. Like when something is provided to us, sometimes we do need to question it. Is it coming from the right sources? Who is doing it? Is the model making a right, fair decision? And I fear that this is a bigger problem now because maybe the average citizen of the world doesn't realize the importance of this. We kind of are fed information from different sources, mainly, videos. I don't want to name the platforms because they will give off my age, and each generation has their own favorite platform to get information from, and most of the time it seems to be the younger generation is looking at these video, whatever, TikTok or whatever you like, but all these are driven by an AI algorithm in terms of what is the content that you're seeing. So at some point, I don't know how that will come, maybe through regulation or so, but to see all the summaries, we are already seeing summaries, right? You go to Facebook, you go to LinkedIn, you go to TikTok, whatever. the order in which you see the videos that you see are very biased towards some rules that they have come up with based on, the information that they have on us. So, and they also have, they are all companies, they want to make profit. So there is a commercial bias to it as well. So to not forget that, and also have tools that will maybe give us similar summaries, but a more unbiased, is what I would have. Could be scientific publication summary, could be news articles that I'm reading. But I fear that we don't have it, and maybe it's up to academics like us to think about these questions. Perhaps so, yeah. Good tools which can maybe help us further in our research and to solve harder questions, and leave the easier ones to AI models maybe.
Let's see if, yeah, I mean, what I would ask AI in my field, I think one issue I have, of course, it's I don't know, we try to understand the universe, which is, a very big and complex problem in astrophysics. And somehow it's not very straightforward to apply an existing model for an application in astronomy, because they are, I don't know, very different in many ways. So they generate a new model, which has to be trained somehow, validated. The validation is very hard, because we cannot go and make samples. And the model is like, the universe is very different to things here. Physics of extreme objects are very extreme. So it's very difficult to model and validate with some experiments here in the lab. So we are a bit blind in terms of validation, and then in terms of training, I feel my issue is that you always need a bigger computer and a model that is very big expensive for the computers, and as the computers grow, more data and the need to train this is also higher. So I like my laptop, and I cannot train this stuff in my laptop. I have to do it in a bigger computer, and for that I need an account, and I need this and this and that. So for me, like, sometimes it's even the computational infrastructure, which is as a standard scientist, is sometimes when you want to develop things from scratch and you want AI to help, you also need to develop an AI model for it, and that requires a big computational infrastructure and some knowledge that it's not very easy to get. So some knowledge and some development. So I would really like to have a simple AI to help with very complicated problem, and I don't know how that works. Yeah, that was my wish list.
I have one too. I have two wishes, my genius. So the first one is probably to have AI that can control AI, meaning that we could eventually enforce some minimum data that you have to submit when you use one of these large language models, that some very large language model will actually use as input, so we can have a clue of what people is doing with it, a little bit. Well anonymized, everything. So we can control and have a sense if people is asking, or if young people is asking too much about something, eventually you might say, well, we have to make people sure they know about this, not necessarily for ChatGPT or whatever else, but from our educational system, kind of thing. And the other is, I would like Inria to give me a gift of a personalized large language model, kind of trained with all my papers and papers of my friends and papers of people I like and I respect, so I can, that could be my personal assistant and help me write papers on my style and do the right citations. So that would be my Inria assistant. Would be perfect. Actually, there is this new tool, I don't know if you guys have used it, it's called Consensus. And Consensus gives you a summary of a topic. If you ask Consensus, tell me about whatever, algebra and fish. And it was, well, algebra and fish are not quite related, but there are some people who actually have done something about this, and these are the key paper. Paper 1 says about this, paper 2 says this and this and this, paper 3 says this and this and this. You go check the papers, and they do say what the model says. So it's like, that's a real treat, so it's like amazing. So those are my...
I'm going to go also to a domain. I remember that I was living in France when Mitterrand was president, and they create and figure that this is a cohabitation. I think this is a good maybe way to do that. Just to arrive at a moment that you just are cohabitants the same place, and that's going to be with the AI products for one side and the human being in another side, just to collaborate in many different ways. But for that, we need just to take, our brain is not perfect. I mean, it's really a machine that creates many things, but it's not so fast. It's very good just to make social interaction, and then we have been done very well. I mean, this part. But the pace, I mean, the time, the clock of the brain is a problem, because we are not following up what happened today in our society, just creating huge amount of data, interfaces, and what we are facing today is a crisis in terms of the stress. Many people now have this burnout, they are in stress, they are in the leave from the university when they are doing his PhD or master, whatever they are. So this is very new, and I think that is, maybe we have reached a level of the evolution of the change in our society, the humanity, that reached a level that the brain is not able to process anymore anything. It's too many things, too many options, that is impossible. So people are dropping off, to the system. And when you drop off in the system, the IA, I mean, artificial product, what's made is just helping you just to keep a little bit more in the run. I'm going to help you. I'm going to help you doing your jobs, your work from the university, and so on. But that also has a limit, because the brain is still the same. So the only way is just to make a pact. We want to do something, but together. That is something that I believe that can be something that just create equilibrium for the future. If not, it's going to be out. I mean, catastrophically out, like Pablo said before. The tipping point is arriving very soon.
Yeah, thank you very much. I think that you pointed something that I personally feel, let's say, at the end the conversation naturally drifted into this, let's say, ChatGPT-like AI, that is destroying something that, or there is something missing in this, is the social aspect, You use this tool alone. So it becomes a dialogue where you stop collaborating because you cook things alone, because you talk to this thing. This is not a collaborative tool, and this is talking about wish lists, It would be awesome that Pablo's LLM is also meant to be used by groups of people that allow us to work together using this like another participant in the conversation, not like your own AI, and so everybody has their own AI in the shoulder doing stuff. And I don't know, I have this feeling for a long time. And also, Adrián just reminded me, I don't know if you know, but the daughter of Karl Marx was married to a Cuban guy that wrote a philosopher, and wrote a book called The Right to be Lazy. And there are, by the way, very interesting writings of Karl Marx getting scandalized because of this guy, the way he was always, you know, a Cuban guy. So, and it's very important that we are saturated all the time. We never have a space where we do nothing, no? That is always saturation. I personally even feel it like if I am not listening to something or doing something, I don't know how to. And it's important to stop and to, as you were saying, Adrián, to lower the, the overload of information, all of that, no? So, let's see. Thank you very much. Thanks. It's a very productive. I am being told that we need to go really quick because there is a reggaeton symposium after us. No, yes. Just joking. Let's take a...
Let's have a moment of silence.
Reggaeton GPT. What was it? Was mine?
Just stay, because I will say just a few words, but please stay. Stay, dear colleagues, dear friends, just a few words before we go. As we draw the curtains of this remarkable edition of the Journées Scientifiques Inria Chile 2024, I have to say that I feel a very profound sense of gratitude, but also inspiration. The past few days have been a testament of the power of science, interdisciplinary collaboration, and the boundless potential of AI, right? We have witnessed brilliant talks from France and Chile converge, sharing knowledge, research, groundbreaking research, sparkling thoughts-provoking discussions, as today, as yesterday, and also Wednesday, and forging new collaborations. And the energy and passion of this room have been palpable. From the depths of fundamental research to the height of real-world impact, we have explored almost the full spectrum of AI, the challenges, and the impacts. But these Journées Scientifiques are more than just a scientific gathering. This year, they are a celebration of the enduring partnership between France and Chile, a partnership rooted in shared values, in mutual respect, and collective commitment to advancing knowledge. As we look to the future, we must remember that the true power of AI lies not in its technical prowess, but in its ability to address humanity's great challenges. Okay. I extend my heartfelt gratitude and thanks to all the speakers, the panelists, the program committee, and the attendees who have made this Journée Scientifique resounding success. And I have a special thanks to the whole team of Inria Chile for the organization. You did it amazing, as always, with the strict deadlines and so much pressure from my side, as always, but thank you so much. And a bit, as we bid farewell to this year's event, let us carry the spirit of innovation, but also the collaboration and the ethical responsibility through science. Let us continue to push the frontiers of AI, and let's wrap up of all these 3 days, fantastic 3 days to the road to the summit, and let's showcase the best of the Franco-Chilean ecosystem of AI in February 2025 in the AI Action Summit in Paris. So thank you again so much for being here. I just want to ask you to come to the stage for a picture, please. Everybody.